Since we were children, movies and stories have shown us a future where humanity travels among the stars, colonizes distant planets, and explores entire galaxies. Spaceships crossing the universe, cities floating in space, humanity scattered across thousands of different worlds. It seems inevitable, doesn't it? It seems like it's just a matter of time until we achieve it. But what if I told you that this entire idea might just be an impossible dream? What if the laws of physics, human biology, and the very nature of the universe conspire against us? Get ready to fall asleep while listening to this video, because we're going to explore an uncomfortable truth that scientists hesitate to admit. We may never leave our small corner of the galaxy. The distances are too great, our bodies are too fragile, and the time required is too long. So the question that changes everything arises. Are we destined to remain trapped here forever, looking at the stars but never reaching them? Subscribe to the channel. Leave your like and comment from which part of the world you're watching. Get comfortable and relax. Let's begin. Have you ever tried to grasp just how big space truly is? Even the simplest explanation fails to capture the mind-boggling scale we're dealing with. When we talk about why humanity will likely remain bound to our solar system, the most fundamental obstacle isn't technology or resources, it's the sheer, uncompromising vastness of space itself. Our nearest stellar neighbour, Proxima Centauri, sits at a distance of 4.24 light-years away. This means light, travelling at 186,000 miles per second, takes over 4 years to reach us from this closest star. To put this in perspective, our fastest spacecraft would take thousands of years to reach even this nearest neighbouring star. The Voyager probes, among humanity's fastest vessels, have been travelling for over 45 years and have barely left our solar system. These cosmic distances create problems that go beyond mere travel time. Any meaningful interstellar mission would need to be sustainable for decades, centuries, or even millennia. The logistics become practically impossible. How do you design technology that works reliably for centuries? How do you plan for repairs, maintenance, and inevitable system failures? Our most sophisticated machines today rarely function without issue for even a decade without significant maintenance. Imagine trying to communicate with an interstellar mission. Radio signals travel at the speed of light, meaning a message sent to a ship just halfway to Proxima Centauri would take over 2 years to receive a reply. Real-time communication would be impossible, and even basic exchanges would stretch over years. This communication delay creates insurmountable challenges for troubleshooting, course corrections, or responding to emergencies. The energy requirements for interstellar travel present another overwhelming obstacle. To reach even a fraction of light speed, say 10%, would require energy equivalent to burning more fuel than exists on Earth. Conventional rocket propulsion simply cannot achieve the necessary velocities for reasonable travel times. More exotic propulsion methods like nuclear pulse propulsion or theoretical antimatter engines face their own tremendous hurdles in efficiency, fuel production, and engineering challenges. Some suggest generation ships as a solution, where multiple generations of humans would live and die during the journey. But this approach introduces complex social, psychological, and biological problems. Would the great-grandchildren of the original crew maintain the mission's purpose? How would such a small, isolated society avoid genetic problems, social collapse, or simply abandoning the original mission objectives? The history of isolated human communities suggests such projects would face significant social deterioration over time. Then there's the relativistic effects that come into play at high speeds. As objects approach the speed of light, time dilation occurs. Any crew travelling at significant fractions of light speed would experience time differently than those on Earth. A journey that might seem like decades to the travellers could represent centuries passing on Earth. By the time they reached their destination, The civilization that sent them might be unrecognizably changed or even extinct. The scale of our galaxy alone is humbling. The Milky Way spans 100,000 light-years across. Even if we could travel at the speed of light, which physics tells us is impossible for material objects, crossing our galaxy would take 100,000 years. The idea of humanity spreading throughout even our own galaxy, let alone to other galaxies millions or billions of light-years away, faces this unyielding reality of distance. Many science fiction scenarios conveniently sidestep these problems with fictional technologies like warp drives, hyperspace, dot, or wormholes. But these remain firmly in the realm of speculation, with most requiring exotic matter or energy conditions that may be physically impossible. Einstein's relativity, one of our most thoroughly tested scientific theories, places the light speed limit as an absolute barrier. No material object can accelerate to or beyond light speed. The energy required approaches infinity as you near the speed of light, creating an impassable barrier. The cosmic calendar helps illustrate the problem. If we compressed the 13.8 billion year history of the universe into a single year, modern humans would appear only in the last minute of December 31st. Our entire recorded history would occupy merely the last few seconds of this cosmic year. Yet the light from distant galaxies we observe today left those galaxies millions or billions of years ago. The universe operates on timescales that dwarf human existence. Our psychological makeup, evolved for life on Earth, further complicates matters. Humans struggle to intuitively grasp very large numbers or vast distances. We evolved to understand distances we could walk in days or weeks, not light years. This cognitive limitation makes it difficult for us to properly plan for the true challenges of interstellar travel. The psychological effects of knowing you're farther from home than any human has ever been, surrounded by empty space for light years in all directions, would be profound and potentially debilitating. Even optimistic projections about technological advancement suggest we're centuries away from having the capabilities needed for interstellar travel, and those projections often rely on breakthroughs that may never occur. Our current understanding of physics suggests some barriers may be truly insurmountable, not just technological challenges waiting to be overcome. The universe has effectively quarantined star systems from one another through the imposition of these vast distances. While we may eventually send robotic probes to nearby stars over the course of centuries, the dream of humans physically travelling between stars, establishing colonies, and becoming a truly interstellar species faces the unyielding reality of cosmic scale. Our destiny may be impressive by human standards, perhaps expanding throughout our solar system, but the gulfs between stars represent a frontier that may forever remain beyond our physical reach. Number sign: the biological fragility of human bodies in space. Look down at your hands for a moment. Every cell in your body has been exquisitely tuned through millions of years of evolution for one specific environment: Earth. This fundamental biological reality forms perhaps the most overlooked obstacle to humanity's interstellar ambitions. Our bodies simply weren't designed for space, and the evidence suggests they may never adapt to it. Space is fundamentally hostile to human life in ways that go far beyond the obvious lack of air and extreme temperatures. The moment an astronaut leaves Earth's protective magnetosphere, they're exposed to cosmic radiation at levels orders of magnitude beyond what we experience on Earth's surface. This high-energy radiation damages DNA directly, significantly increasing cancer risk and causing cellular damage throughout the body. Current estimates suggest a mission to Mars would expose astronauts to their lifetime limit of acceptable radiation. Now imagine a journey lasting decades or centuries to reach another star. Shielding presents its own impossible trade-offs. Effective radiation shielding requires massive amounts of material, typically water, concrete, or metal, that would make spacecraft prohibitively heavy for interstellar travel. The energy requirements to accelerate such heavily shielded vessels would compound the already overwhelming propulsion challenges. Some studies suggest that to provide Earth-like radiation protection would require shields several meters thick, adding thousands of tons to spacecraft mass, even if we could solve the radiation problem. The absence of gravity wreaks havoc on the human body. Astronauts on the International Space Station experience significant bone density loss, as much as 1.5% per month, despite rigorous daily exercise regimens designed to mitigate these effects. Over years, this could lead to catastrophic skeletal deterioration. Muscle atrophy occurs even faster, with significant strength loss occurring within weeks. The cardiovascular system similarly depends on gravity. In microgravity, blood and fluid redistribution causes facial swelling, changes to blood pressure regulation, and reduced heart efficiency. The heart, no longer having to pump against gravity, actually loses muscle mass. Extended exposure leads to arrhythmias and potential heart failure. Studies of astronauts returning from even relatively short missions show concerning cardiovascular changes that might become permanent during longer journeys. Our vision system also deteriorates in space. Many astronauts experience what NASA calls spaceflight-associated neuroocular syndrome, with symptoms including flattening of the eyeball, swelling of the optic nerve, and vision changes that can become permanent. The causes appear linked to fluid shifts in microgravity that increase pressure in the brain and eyes. For a mission spanning decades, the cumulative damage could lead to blindness. The immune system becomes compromised in space environments as well. Studies show dormant viruses reactivate in astronauts' bodies during spaceflight, while immune cell function becomes impaired. This immunosuppression would make long-duration crews vulnerable to infections, especially in the closed environment of a spacecraft where pathogens could easily spread among the limited population. Our digestive and metabolic systems evolved specifically for Earth's gravity. In space, digestive efficiency decreases, nutrient absorption changes, and metabolic alterations occur that science doesn't fully understand yet. Long-term nutritional deficiencies would be inevitable on multi-year journeys, leading to various health problems from scurvy to osteoporosis. The psychological impacts of space travel represent another biological barrier. Human brains evolved in environments with open horizons, changing seasons, diverse ecosystems, and large social groups. The extreme confinement, isolation, monotony, and artificial environments of long-duration spaceflight trigger psychological disorders including depression, anxiety, sleep disturbances, and cognitive impairment. The longest continuous human spaceflight, 437 days, already pushes the limits of psychological endurance. Extending this to years or decades seems psychologically untenable. Reproduction, essential for truly multi-generational voyages, faces tremendous hurdles in space. Studies with animals show that radiation exposure causes fertility problems and developmental abnormalities in embryos. Human fetal development relies on gravity for proper bone and muscle formation. Pregnancy in microgravity might prove impossible, or could result in children with severe developmental issues. Even if children could be born healthy, growing up in microgravity would likely result in bodies unable to function if they ever reached a planetary surface with significant gravity. Sleep, critical for cognitive function and physical health, deteriorates in space. Astronauts on the International Space Station typically sleep poorly, with disrupted circadian rhythms due to the absence of normal day-night cycles. They experience 16 sunrises and sunsets daily as they orbit Earth. For interstellar travelers, artificial lighting would need to perfectly replicate natural conditions, a challenge we haven't solved even in terrestrial environments. Our sensory systems depend on Earth's specific conditions as well. The vestibular system in our inner ear, which governs balance and spatial orientation, becomes severely disoriented in microgravity. while adaptation occurs over weeks. This system evolved specifically for Earth's gravitational environment. Permanent changes to spatial processing in the brain occur during long-duration spaceflight, some of which persist after return to Earth. Even our microbiome, the trillions of bacteria that inhabit our bodies and play crucial roles in digestion, immunity, and even mental health, changes dramatically in space. These microbial communities evolved alongside humans in Earth's environment, and their disruption in space causes health problems we're only beginning to understand. Genetic damage from radiation accumulates over time and can be passed to subsequent generations. A multi-generational spacecraft might experience increasing genetic damage in its population, leading to higher rates of cancer, birth defects, and other genetic disorders with each new generation born in space. Some suggest genetic engineering or cybernetic enhancements as solutions to these biological limitations. However, the complexity of the human genome and our limited understanding of how genes interact means we're centuries away from safely engineering humans for space. Even with advanced bioengineering, the fundamental biological processes that sustain us evolved specifically for Earth's gravity, atmosphere, radiation levels, and biosphere. The human body is not a machine that can be arbitrarily redesigned. It's the product of an unimaginably complex evolutionary process optimized for one specific planet. As we venture farther from Earth for longer periods, we increasingly understand that we are, in a very literal biological sense, Earthlings. Our cells, systems, and psyches are Earth-derived and Earth-dependent. While technology may eventually help us survive in space for longer periods, the evidence increasingly suggests that truly long-term existence away from our home planet may remain beyond the biological capabilities of Homo sapiens. Beyond the biological limitations of our bodies, the challenges of interstellar travel extend into the realm of fundamental physics and energy requirements. While science fiction often makes star travel seem like just another engineering problem to solve, the actual energy demands reveal a more sobering reality that forms another substantial barrier to our interstellar aspirations. Let's consider what it would actually take to propel a spacecraft to the speeds necessary for reasonable interstellar travel times. To reach even the nearest star system within a human lifetime would require travelling at a significant fraction of light speed, at least 10%. The energy required to accelerate even a modest 1,000-ton spacecraft to such velocities is staggering. Calculations show it would require approximately 450 petajoules, energy equivalent to the entire world's electricity production for several months, concentrated into a single spacecraft. Conventional rocket propulsion is immediately disqualified for such missions. Chemical rockets, the technology that took us to the moon, operate by combusting fuel and oxidizer. Even the most efficient chemical reactions release only a tiny fraction of the energy needed for interstellar velocities. The fundamental chemistry limits the exhaust velocity, meaning you would need millions of times more fuel than payload, a mathematical impossibility under any realistic scenario. Some point to nuclear propulsion as the answer, but even these technologies face severe limitations. Nuclear fission, while offering energy density roughly 1,000,000 times greater than chemical fuels, still falls orders of magnitude short of what interstellar travel demands. Nuclear fusion, though more promising in theory, presents enormous engineering challenges. After more than 70 years of research, we still haven't achieved sustained fusion power generation on Earth, let alone compact fusion engines for spacecraft. The theoretical ultimate in propulsion technology, antimatter engines, presents its own insurmountable paradox. Antimatter annihilation releases energy with perfect efficiency, converting mass directly to energy according to Einstein's famous equation. However, antimatter doesn't exist naturally in our universe in usable quantities. It must be manufactured, and current methods require approximately 10,000 times more energy to create antimatter than you get back when you use it. This represents a fundamental energy deficit that no engineering can overcome. Even if we could somehow produce antimatter efficiently, containing it presents another seemingly insurmountable problem. Antimatter annihilates instantly upon contact with normal matter, requiring perfect magnetic containment systems that would themselves require substantial energy to maintain. The slightest containment failure would result in catastrophic explosion, hardly a risk worth taking on a multi-decade mission with no possibility of rescue. The physics of rocket propulsion itself creates another barrier through what's known as the Tsiolkovsky rocket equation. This mathematical relationship shows that the faster you want to go, the exponentially more fuel you need to carry. But that additional fuel adds mass, which requires even more fuel to accelerate, creating a vicious cycle of diminishing returns for interstellar velocities. This equation becomes particularly punishing. You'd need a fuel mass millions of times greater than your payload. Some proposed solutions like solar sails or beamed propulsion attempt to leave the fuel behind, using external energy sources to drive the spacecraft. But these approaches face their own fundamental limitations. Solar sails become ineffective beyond our solar system as light intensity drops with the square of distance from the sun. Beamed propulsion concepts, where ground-based lasers push spacecraft via radiation pressure, would require laser arrays of unprecedented scale, consuming power equivalent to our entire planetary energy production. Theoretical exotic propulsion methods like warp drives or space-time manipulation remain firmly in the realm of speculation. These concepts require exotic forms of matter or energy, like negative mass or dark energy control, that may be physically impossible according to our understanding of the universe. Most require quantities of energy comparable to the output of entire stars. The brutal reality of interstellar energetics is that we're not talking about incremental improvements to existing technology. We're facing energy requirements that exceed our planetary capabilities by many orders of magnitude. It's not like developing more efficient airplane engines. It's more akin to asking a medieval society to build a nuclear power plant. The gap between what we can harness and what interstellar travel demands may represent a truly insurmountable barrier. All these energy challenges assume we're only trying to reach the nearest star. To truly become an interstellar species capable of exploring multiple star systems would multiply these energy requirements many times over. The laws of physics and thermodynamics aren't just temporary technological hurdles, they represent fundamental constraints on what material civilizations can achieve, regardless of their technological sophistication. Even if we somehow solved the propulsion problem, the energy requirements for life support, communications, and shielding would add substantial additional energy demands to any interstellar mission. Every joule of energy used aboard a spacecraft ultimately becomes waste heat that must be radiated away, another engineering challenge that scales with energy use. In the vacuum of space, getting rid of excess heat becomes extraordinarily difficult for high-energy systems. Perhaps the most sobering aspect of the energy paradox is that it may represent a universal filter explaining the apparent absence of interstellar civilizations. If the energy requirements for interstellar travel are genuinely beyond what any planetary civilization can achieve, it would explain why we see no evidence of alien visitation despite the billions of stars and potentially habitable planets in our galaxy. The energy barrier may be nature's way of keeping civilizations bound to their home star systems. Beyond the daunting physical and energy barriers of interstellar travel lies another equally formidable obstacle: the economic impossibility of such ventures. While we often discuss space exploration in terms of technology, the financial realities of interstellar missions reveal challenges that may be even more insurmountable than the engineering problems. The costs associated with interstellar travel would be astronomical in the most literal sense. Consider that the International Space Station, orbiting just 250 miles above Earth, cost approximately $150 billion over its lifetime. The James Webb Space Telescope, operating at a distance of 1 million miles from Earth, cost around $10 billion. Now try to estimate the cost of a spacecraft designed to travel 4.2 light-years to our nearest stellar neighbour, a distance nearly 30 million times farther than the Webb telescope. The research and development costs alone for technologies that don't yet exist would likely exceed the gross domestic product of the entire Earth. Developing practical fusion propulsion, long-duration life support, radiation shielding, and all the other necessary technologies would require decades or centuries of sustained investment before construction could even begin. Each of these technologies represents not just an incremental improvement on existing capabilities, but fundamental breakthroughs that have eluded us despite decades of effort. Once designed, the construction of an interstellar vessel would require industrial capabilities far beyond our current capacity. It would likely need to be assembled in space, requiring a space-based industrial infrastructure that itself would cost trillions to develop. The materials required would likely include rare elements that are already in short supply for earthly technologies. The quantities of titanium, beryllium, uranium, and other specialized materials would strain global production capacity. Economically speaking, interstellar missions present an impossible investment case. All conventional economic models rely on some return on investment within a reasonable time frame. Yet interstellar missions would require enormous upfront costs with literally no economic return for centuries, if ever. No private enterprise could justify such an investment, and even nations would struggle to allocate resources to a project whose benefits might not be realized for dozens of generations. This time frame creates another economic impossibility: sustaining funding over multiple generations. Historical evidence shows that even decade-long projects frequently face budget cuts, cancellations, or radical restructuring as political priorities shift. The Apollo program, despite its success, saw its later missions cancelled due to changing budget priorities. The International Space Station required constant political reinforcement to maintain funding across multiple administrations. Now imagine trying to maintain financial and political commitment to a project that might not see completion for a century or more. International cooperation, often proposed as a solution to the enormous costs, introduces its own complications. Geopolitical rivalries, competing national interests, and different economic systems make long-term international scientific collaboration extraordinarily difficult. The International Space Station represents the high watermark of such cooperation, but even this required constant diplomatic effort to maintain. Scaling such cooperation to the much larger and longer-term requirements of an interstellar mission seems politically unfeasible. The opportunity costs of interstellar investment create another economic barrier. Every dollar, yuan, or euro spent on developing interstellar capabilities is a dollar not spent on addressing immediate human needs like healthcare, education, infrastructure, or combating climate change. As long as pressing terrestrial problems exist, diverting significant resources to interstellar exploration would face overwhelming ethical objections. Economic volatility adds another layer of impossibility. Our global economic system experiences regular cycles of growth and recession, as well as occasional financial crises. These fluctuations make maintaining consistent funding levels for even decade-long projects challenging. A century-long development timeline would inevitably span multiple major economic downturns, during which funding for speculative long-term projects is typically slashed first. The economics of scale work against interstellar missions as well. Unlike commercial technologies that become cheaper as they're produced in quantity, interstellar missions would likely be one-off or extremely limited production items. The research, development, and construction costs would be amortized across very few units, making each mission prohibitively expensive. There's no path to making interstellar travel economically accessible through mass production or economies of scale. From a resource allocation perspective, interstellar travel represents perhaps the most extreme example of diminishing returns imaginable. The astronomical costs would yield benefits only for a tiny number of humans, the few hundred or thousand who might actually make the journey. This stands in stark contrast to investments in medicine, renewable energy, or other technologies that could benefit billions of people for generations. Perhaps most fundamentally, interstellar economics suffers from a temporal mismatch between human economic systems and cosmic timescales. Our economic institutions, banks, governments, corporations, operate on quarterly, annual, or at most decadal planning horizons. They're fundamentally incapable of rational investment decision-making when the payoff might come centuries in the future. No economic system yet devised can properly value outcomes hundreds of years in the future against present costs. The economic realities suggest that humanity will remain bound to our solar system not just because of physical limitations, but because of economic ones. While our technology might eventually advance to theoretically allow interstellar travel, the economic case for actually funding such missions may never materialize. In a universe governed as much by economics as by physics, the stars may remain perpetually out of reach, not because we couldn't someday build the ships to reach them, but because we could never pay for them. The economic impossibility of interstellar travel has led many theorists to propose alternative approaches that might circumvent the need for immediate returns on investment. One of the most frequently discussed solutions is the generation ship, a vessel designed not to return to Earth or even reach its destination within the lifetime of its original crew, but to sustain multiple generations of humans during a journey spanning centuries. While this approach seems to solve the speed problem, examining the social and psychological realities of generation ships reveals new layers of insurmountable challenges. A generation ship would essentially be a miniature, sealed society, a habitat containing everything needed to sustain human life for centuries without external resources. The concept sounds reasonable at first glance. If we can't make the ship go faster, we simply accept the journey will take longer than a human lifetime. The original crew would live, reproduce, grow old, and die aboard the vessel, with their children, grandchildren, and subsequent generations continuing the mission until eventually, descendants of the original crew would arrive at the destination star system. However, human societies don't function like machines that can be programmed to maintain a single purpose across centuries. The social dynamics of isolated, confined populations reveal profound problems that would doom such missions. Studies of isolated human communities throughout history show consistent patterns of cultural drift. Within just 2 or 3 generations, the values, priorities, and beliefs of a society can transform dramatically. Religious communities founded on specific principles frequently see their descendants abandon or radically reinterpret those principles within a century. Applied to a generation ship, this cultural drift creates an existential problem. Why would the great-grandchildren of the original crew maintain commitment to a mission they never chose? Born into what amounts to a sealed space habitat, the only world they've ever known, these later generations would have no personal connection to Earth or the original mission objectives. Their entire lived reality would be the internal environment of the ship. The notion that they should sacrifice their lives travelling through empty space for a destination they'll never see, to fulfill a mission created by long-dead ancestors, defies everything we understand about human psychology and social dynamics. This isn't merely speculation. Earth-based experiments with isolated habitats like Biosphere 2 have demonstrated the extreme difficulty of maintaining even short-term isolated human habitats. The 2-year Biosphere 2 mission was intended to demonstrate the viability of self-contained ecosystems but was plagued by social conflict, psychological stress, and factionalism among its small crew of just 8 people. Scaling this to decades or centuries multiplies these problems exponentially. Small, isolated populations also face severe genetic challenges. A viable generation ship would need to carry enough people to maintain genetic diversity and avoid the health problems associated with inbreeding. Population geneticists suggest a minimum viable population of approximately 2,000 individuals to maintain genetic health over many generations without external genetic input. This minimum population size dramatically increases the required scale of any generation ship, further exacerbating the already impossible economic and engineering challenges. The governance of a generation ship presents another unsolvable problem. What political system could remain stable over centuries in a closed environment with limited resources? Historical precedent suggests that isolated societies under stress tend toward authoritarian governance structures, the absolute physical boundaries of a spacecraft, where no one can leave or escape the governing authority, would create conditions ripe for oppression. With no external oversight or accountability, what would prevent the emergence of dictatorial control over subsequent generations? Psychological health represents another critical barrier. Humans evolved in open environments with natural scenery, changing seasons, diverse ecosystems, and the company of thousands of other humans and species. The long-term psychological effects of confinement in an artificial habitat are already evident in much shorter missions. Astronauts on the International Space Station frequently report symptoms of depression, anxiety, and cognitive changes despite knowing their missions last only months, extending this to lifelong confinement. With no possibility of ever experiencing an open sky or natural environment, would create psychological burdens no human population has ever endured. The problem compounds across generations. While the first crew would at least have memories of Earth to sustain them, their children would know only second-hand accounts, and subsequent generations would be increasingly disconnected from the natural environments humans evolved to inhabit. The psychological consequences of being born, living, and dying in an entirely artificial environment are unknown but likely severe. Resource management over centuries introduces another critical vulnerability. Any closed system experiences entropy and degradation over time. Materials break down, systems fail, and resources are lost through inefficiencies. A generation ship would need to maintain perfect or near-perfect recycling of air, water, and nutrients for centuries, a level of efficiency that exceeds anything we've achieved in even short-term closed systems on Earth. The margin for error approaches zero, as the consequences of significant system failures in interstellar space would be extinction for the entire population. Perhaps the most fundamental problem with generation ships is the ethical question they present. What right does one generation have to commit their unborn descendants to lives confined within a spacecraft? The children and grandchildren born on such vessels never consented to participate in the mission. They would effectively be born into a prison from which there is no escape, their entire lives predetermined by decisions made before their birth. This represents a level of determination over future lives that we generally consider ethically unacceptable in other contexts. The generation ship concept ultimately reveals a profound mismatch between human social reality and the requirements of interstellar travel. We aren't machines that can be programmed to maintain a single purpose across centuries of isolation. We're social beings whose cultures, values, and priorities naturally evolve and transform across generations. The idea that we could create a miniature society that would maintain its original mission focus intact across centuries contradicts everything we understand about human social dynamics. The generation ship, far from being a solution to the interstellar travel problem, merely transforms technical challenges into social and psychological ones that may be even more fundamentally unsolvable. Faced with the daunting challenges of generation ships, some theorists have proposed an alternative approach: suspended animation or human hibernation. Instead of living through the centuries-long journey, the crew could be placed in a state of biological suspension, effectively sleeping through the voyage and awakening only upon reaching their destination. This approach seemingly sidesteps many of the social and psychological problems of generation ships, while also reducing life support requirements. However, the biological realities of suspended animation reveal this solution to be equally unviable for interstellar journeys. The fundamental challenge is that humans, unlike some animal species, have no natural biological mechanism for long-term hibernation. Bears and certain other mammals can reduce their metabolic rate during winter months. But even these natural hibernators maintain critical biological functions throughout their dormancy. Their cells continue metabolizing, albeit at reduced rates, and their bodies periodically warm to prevent tissue damage. True suspended animation, the complete halting of metabolic processes while maintaining the possibility of future revival, simply doesn't exist in nature for complex organisms like humans. Cryonics, the practice of preserving human bodies at extremely low temperatures, is often suggested as a technological solution. The concept involves cooling the human body to near liquid nitrogen temperatures around -196 degrees Celsius to halt all biological activity, preserving the body until future revival. However, the freezing process itself causes catastrophic cellular damage in humans. When water freezes, it forms ice crystals that physically rupture cell membranes throughout the body. This isn't a technological limitation we might someday overcome, it's basic physics and biology. To address the ice crystal problem, cryonics researchers have developed vitrification techniques using cryoprotectant chemicals that allow water to solidify in a glass-like state without crystallization. While this shows some promise for preserving small tissue samples, scaling it to entire human bodies introduces insurmountable problems. The cryoprotectant chemicals themselves are toxic at the concentrations needed for effective vitrification. They must permeate every cell in the body uniformly, an impossible requirement for large, complex organisms with diverse tissue types and varying rates of chemical penetration. Even if perfect vitrification could somehow be achieved, the revival process presents equally formidable challenges. Warming must occur uniformly throughout the body to prevent thermal stress and fracturing. The cryoprotectant chemicals must then be completely removed from every cell before normal metabolism resumes, as they would be toxic at body temperature. The technical complexity of this process for a complete human body exceeds anything remotely possible with current or foreseeable technology. The track record of cryonics research underscores these difficulties. Despite decades of research and numerous preserved human bodies, not a single human cell, let alone a complete organ or body, has ever been successfully cryopreserved and revived with normal function. Even simple mammalian organs like kidneys suffer irreparable damage during current cryopreservation procedures. The gap between preserving a few specialized cell types, which has been achieved, and preserving the integrated function of trillions of cells in hundreds of different tissues, is not a matter of incremental improvement. It represents a qualitative leap that may be biologically impossible. Beyond these technical challenges lies a more fundamental biological reality. Suspended animation doesn't truly pause biological time. Even if metabolism could be dramatically reduced, subtle degradation processes continue. DNA experiences damage from background radiation and chemical degradation. Proteins denature slowly over time. Cellular membranes break down through oxidation and other processes. Over the decades or centuries required for interstellar travel, these cumulative effects would render revival impossible, regardless of the initial preservation technique. The energy requirements for maintaining cryogenic temperatures over centuries create another insurmountable obstacle. Cooling systems would need to function flawlessly for the entire journey, as even brief warming periods would cause catastrophic damage to preserved tissues. The energy needed to maintain these temperatures, especially in the vacuum of space where heat rejection is challenging, would constitute a significant portion of the spacecraft's power budget, further straining the already impossible energy equations of interstellar travel. Some researchers have proposed alternative approaches like chemical suspended animation, using drugs to induce a torpor state with reduced metabolism, while some promising research exists for short-duration medical applications, hours or days. Extending such techniques to years or decades faces fundamental metabolic barriers. The human body cannot sustain even moderately reduced metabolism for extended periods without experiencing muscle atrophy, bone density loss, cardiovascular deterioration, and other degenerative conditions. Our biology simply isn't designed for hibernation. The psychological aspects of suspended animation present additional concerns. Even if the physical body could somehow be preserved, the effects on the brain of years of inactivity remain unknown but potentially devastating. Memory, personality, and cognitive function depend on ongoing neurological processes and regular reinforcement of neural pathways. The notion that consciousness could be switched off and then perfectly restored decades later contradicts our understanding of how the brain maintains continuity of function and identity. If multiple crew members were to be revived periodically for maintenance and monitoring before returning to suspension, they would face profound psychological challenges. Awakening to find decades had passed, with family and friends on Earth having aged or died, would create psychological trauma unlike anything humans have experienced. The isolation of being briefly conscious in deep space, performing maintenance tasks, and then returning to suspension would likely cause severe psychological distress with each cycle. The ethical dimensions of suspended animation mirror some of those facing generation ships. What happens if the technology fails during the journey? What if revival proves impossible upon reaching the destination? The crew would have effectively died at the beginning of the mission, rendering the entire journey pointless. The consent provided before departure would be based on assumptions about revival that might prove false, raising questions about informed consent for what amounts to an experimental medical procedure with likely fatal outcomes. The scientific consensus among biologists and medical researchers who study suspended animation is clear. While limited forms of metabolic reduction might someday be possible for short durations, true long-term suspended animation for humans remains firmly in the realm of science fiction. The biological barriers aren't just technological limitations awaiting clever solutions, they represent fundamental constraints of human physiology that evolved specifically for continuous, active metabolism in Earth-like conditions. Just as we cannot engineer humans to photosynthesize or breathe water, we likely cannot re-engineer the integrated complexity of human biology to survive suspended animation for the durations interstellar travel would require. The biological limitations of suspended animation reveal another profound challenge facing interstellar travel, even if we could somehow preserve human bodies for the journey. The laws of physics themselves present barriers that no amount of technological progress can overcome. Most fundamental among these is the universal speed limit encoded in Einstein's theory of relativity, the speed of light. When we discuss interstellar travel, we often talk about the problem as if it's merely a matter of developing faster propulsion systems. Yet Einstein's special relativity, one of the most thoroughly tested and confirmed theories in all of science, establishes the speed of light, approximately 670 million miles per hour, as an absolute cosmic speed limit. This isn't a technological hurdle we might eventually overcome, but a fundamental property of space-time itself. The implications of this speed limit are profound and inescapable. Even if we could somehow accelerate a spacecraft to 99% of light speed, far beyond anything currently possible, the journey to even the nearest star system would still take over 4 years from the perspective of observers on Earth. For more distant potential destinations with possibly habitable planets, travel times would extend to decades or centuries even at these near light speeds. What makes the light speed barrier particularly unyielding is the physics of acceleration. As an object with mass approaches light speed, its energy requirements don't increase linearly but exponentially. The closer you get to light speed, the more energy is required for each additional increment of acceleration. The mathematics are uncompromising. To accelerate an object with mass to exactly light speed would require infinite energy. Not just a lot of energy, not just more than we currently can produce, but literally infinite energy. A mathematical impossibility. This creates what physicists call the relativistic mass increase problem. As objects approach light speed, they effectively become heavier from the perspective of any force trying to accelerate them further. At 90% of light speed, an object's effective mass is more than double its rest mass. at 99%. It's 7 times heavier. At 99.9%, it's 22 times its original mass. This creates an insurmountable energy curve. Each additional percentage point closer to light speed requires exponentially more energy than the last. Some speculate about theoretical loopholes like warp drives, which would theoretically contract space-time in front of a vessel and expand it behind, allowing effective faster-than-light travel without technically breaking the light speed barrier locally. However, these concepts require exotic forms of matter and energy that may not exist in reality. The theoretical Alcubierre drive would require negative energy density, something never observed in nature and possibly fundamentally forbidden by quantum physics. Other proposals require manipulating hypothetical extra dimensions or creating stable wormholes, concepts that remain purely mathematical with no evidence they could be physically realized, even if we accept the light speed limit and simply plan to travel below it. Relativity introduces another complication: time dilation. As objects move close to light speed relative to other objects, they experience time at different rates. A spacecraft travelling at significant fractions of light speed would experience less time passing than observers back on Earth. While this might seem beneficial for the crew, effectively shortening their subjective journey time, it creates profound complications for any coordinated interstellar mission. A one-way trip to a star 20 light-years away at 80% of light speed would take 25 years as measured from Earth. But for the crew, only 15 years would pass due to time dilation. This temporal disconnection makes real-time communication impossible and creates profound logistical problems for mission coordination. Any transmitted information would be years or decades out of date by the time it arrived. For the crew themselves, time dilation creates its own existential challenge. Upon returning from a round trip at relativistic speeds, they might find that while they aged perhaps 30 years subjectively, Earth has aged 50 or 60 years. Their contemporaries would be elderly or dead, and human civilization itself might have transformed dramatically during their absence. This temporal exile is yet another barrier to meaningful interstellar exploration. Perhaps most fundamentally, the light speed limit means that even in the most optimistic scenarios, human presence would be limited to a tiny bubble within the vast expanse of our galaxy. The Milky Way is 100,000 light-years across, even with hypothetical ships travelling at significant fractions of light speed. Exploring even a modest portion of our galaxy would take longer than human civilization has existed. The dream of humans becoming a truly galactic species, spread across thousands or millions of star systems, faces this immutable barrier of cosmic distance combined with finite speed. The mathematics of special relativity have been tested countless times through particle accelerators, atomic clocks on airplanes, and observations of cosmic phenomena. Each test has confirmed Einstein's equations with increasing precision. There is no serious scientific debate about the reality of the light speed limit. It appears to be woven into the very fabric of reality. While science has occasionally overthrown seemingly fundamental barriers in the past, the light speed limit is qualitatively different. It's not merely an engineering challenge, but a fundamental property of space-time itself. Beyond the light speed barrier lies another, equally formidable obstacle to interstellar travel: the constant bombardment of deadly radiation that permeates interstellar space. While we can shield ourselves relatively effectively from radiation on Earth thanks to our atmosphere and magnetic field, the void between stars presents a radiation environment incompatible with long-term human survival. Space radiation comes in multiple forms, each presenting its own dangers. Galactic cosmic rays consist of atomic nuclei, primarily hydrogen, helium, and heavier elements accelerated to near light speed by distant cosmic events like supernovae. Solar radiation includes energetic particles ejected by our Sun during solar flares and coronal mass ejections. Both types can penetrate spacecraft hulls and human tissue, causing cellular damage, increased cancer risk, and potentially fatal radiation sickness. What makes cosmic radiation particularly dangerous is its high energy. Many cosmic ray particles carry energies millions of times greater than the radiation used in medical X-rays. When these particles hit human tissue, they can break DNA strands and generate secondary particles that cause additional damage. Unlike lower energy radiation that might be stopped by thin shielding, these high energy particles pass through conventional materials with ease, making them exceptionally difficult to block. The health effects of space radiation exposure are cumulative and devastating for long-duration missions. NASA and other space agencies carefully track astronaut radiation exposure and limit mission durations based on accumulated dose. Current estimates suggest a mission to Mars would expose astronauts to their career lifetime limit of acceptable radiation. Extending this to the years or decades required for interstellar travel would result in radiation exposure far beyond anything compatible with human survival. Shielding presents an impossible trade-off for interstellar spacecraft. Effective radiation shields require substantial mass, typically water, polyethylene, DOT, or other hydrogen-rich materials. The most effective shields would need to be several meters thick to approach Earth-like protection levels. Yet every kilogram of shielding requires additional propulsion energy, creating a compounding problem with the already impossible energy requirements for interstellar travel. The heavier the shield, the more fuel required, which makes the vessel larger, which requires more shielding, a vicious cycle of increasing mass. Some researchers have proposed active shielding using electromagnetic fields similar to Earth's magnetosphere. While theoretically promising, such systems would require enormous amounts of energy to maintain fields strong enough to deflect high-energy cosmic particles. The superconducting magnets needed for such shields add their own mass penalties and create additional engineering challenges for long-term reliability. The radiation problem worsens once a spacecraft ventures beyond the protective bubble of our Sun's heliosphere, the region where the solar wind dominates over interstellar particles. This boundary, which our Voyager probes crossed at a distance of roughly 11 billion miles from the Sun, marks the transition to true interstellar space where radiation levels are even higher than in our solar system. Beyond the health effects on human crews, radiation creates severe problems for spacecraft systems themselves. Electronics, particularly the sensitive microchips that would control all aspects of an interstellar mission, are vulnerable to radiation damage. When high-energy particles hit electronic components, they can cause bit flips that corrupt data or more permanent damage that degrades performance over time. Even with radiation-hardened electronics, which are heavier, more power-hungry, and less capable than standard versions, the cumulative damage over decades would likely cause critical system failures. Biological solutions to the radiation problem, such as radiation-resistant organisms like tardigrades or certain bacteria, offer limited insight but few practical solutions. The DNA repair mechanisms these organisms employ work for their simple cellular structures but can't be easily transferred to the vastly more complex human body. Genetic engineering to increase radiation resistance in humans would require fundamental changes to our cellular biology far beyond current or foreseeable capabilities. Perhaps the most sobering aspect of the radiation problem is its inevitability. Unlike technological challenges that might be overcome with sufficient ingenuity, cosmic radiation is a fundamental feature of the interstellar environment. It has bombarded the space between stars for billions of years and will continue to do so for billions more. There is no foreseeable technology that could completely eliminate this radiation or its effects on human biology. The combination of radiation exposure and mission duration creates a double bind for interstellar travel. Faster ships would reduce exposure time but require more energy. More heavily shielded ships would reduce exposure rates but would be heavier and therefore slower. This creates a fundamental equation where radiation exposure cannot be reduced below lethal levels without making other mission parameters impossible. For unmanned probes, radiation presents serious but potentially manageable problems through redundant systems and radiation-hardened electronics. But for human crews, The radiation of interstellar space represents a biological barrier that may be truly insurmountable. Our bodies evolved under the protective shields of Earth's magnetic field and atmosphere. The unfiltered radiation environment of deep space is as fundamentally hostile to human life as the vacuum itself, and possibly even harder to mitigate through technology alone, even if we could somehow overcome the deadly radiation permeating interstellar space. Another sobering reality awaits any would-be interstellar explorers: the stunning lack of truly habitable destinations within reach. Despite the discovery of thousands of exoplanets in recent decades, the findings have actually diminished rather than enhanced our hopes for finding easily habitable worlds nearby. When astronomers began discovering planets around other stars in the 1990s, there was widespread optimism that we'd quickly find Earth twins, planets similar in size, composition, and climate to our homeworld. The reality has proven far more complicated. Most exoplanets discovered to date are inhospitable gas giants, scorching hot worlds orbiting close to their stars, or frozen worlds far from stellar warmth. The much-discussed habitable zone, the region around a star where temperatures might allow liquid water, has turned out to be a profoundly simplistic concept that ignores dozens of other habitability factors. Consider the planets in our own cosmic backyard. Mars, which sits at the edge of our Sun's habitable zone, has a surface pressure less than 1% of Earth's, almost no magnetic field to block radiation, and temperature swings of over 100 degrees Celsius between day and night. Venus, also technically within the habitable zone, has a runaway greenhouse atmosphere with surface temperatures hot enough to melt lead and crushing atmospheric pressure 90 times greater than Earth's. Neither planet is remotely habitable without extraordinary technological intervention beyond anything we can currently achieve. The exoplanets we've found around other stars present even greater challenges. Proxima Centauri b, the nearest known exoplanet at just 4.2 light-years away, orbits a red dwarf star that bathes it in deadly flares and radiation levels far exceeding anything in our solar system. It's likely tidally locked, meaning one side perpetually faces its star while the other remains in permanent darkness, creating extreme temperature differences incompatible with Earth-like life. Similar problems plague most planets discovered around red dwarf stars, which make up the majority of stars in our galaxy. Water, essential for life as we know it, presents another critical challenge. While astronomers can sometimes detect water vapor in exoplanet atmospheres, determining the presence of surface water, oceans, lakes, or rivers remains beyond our current observational capabilities. Many apparently rocky planets might be completely dry or have toxic chemical compositions in their surface liquids. The water worlds, with global oceans hundreds of miles deep, would have seafloors under such enormous pressure that the water would form exotic high-pressure ice, preventing the crucial geological cycles that make Earth habitable. The atmospheric composition of exoplanets presents additional barriers to habitability. Many rocky exoplanets have been found with atmospheres dominated by carbon dioxide, hydrogen, or other gases toxic to humans. Oxygen-rich atmospheres like Earth's are likely extremely rare, as Earth's oxygen comes primarily from biological activity, not geological processes, without an existing biosphere already producing oxygen for billions of years. Most rocky planets would have atmospheres humans couldn't breathe. Gravity poses another fundamental problem. Planets just 10% larger than Earth could have surface gravity significantly stronger than what human physiology evolved to handle. Living permanently in high-gravity environments would cause cardiovascular strain, skeletal problems, and other health issues. Conversely, planets much smaller than Earth might lack the gravity needed to retain a substantial atmosphere, resulting in conditions more like Mars or even our airless moon. The magnetic fields protecting Earth from cosmic radiation result from our planet's specific internal composition and rotation rate. Many exoplanets, particularly those tidally locked to their stars, would lack similar protection, exposing their surfaces to sterilizing radiation levels incompatible with complex life. The complex interaction between a planet's core composition, rotation, and magnetic field generation is difficult to predict, but crucial for habitability. Geological activity presents another habitability requirement often overlooked. Earth's plate tectonics regulates our climate over long timescales by cycling carbon between the atmosphere and the planet's interior, preventing both runaway heating and cooling. Planets without similar geological processes often end up like Venus, trapped in a runaway greenhouse effect, or Mars, having lost most of its atmosphere without a recycling mechanism. The factors determining whether a planet will have Earth-like geological activity depend on complex internal compositions that we cannot directly observe in exoplanets. The day-night cycle that Earth organisms evolved with results from our specific rotation period. Planets with much longer days and nights would experience extreme temperature fluctuations, while tidally locked planets would have permanent hot and cold zones. Biological rhythms deeply embedded in Earth organisms depend on our roughly 24-hour day. Human physiology, from sleep cycles to hormonal rhythms, is fundamentally tied to this day length, making adaptation to radically different day-night cycles problematic. Seasonality, resulting from Earth's axial tilt, drives countless biological processes from migration to reproduction cycles. Planets with different axial tilts might experience extremely severe seasons or none at all, creating environmental conditions Earth organisms aren't adapted to handle. The stability of a planet's axial tilt over time, maintained in Earth's case partly by our unusually large moon, is another factor critical for long-term climate stability. Perhaps most fundamentally, the biochemical compatibility between humans and any alien environment would likely be non-existent. Even if we found a planet with the right temperature, atmosphere, and gravity, its native biochemistry, shaped by billions of years of independent evolution, would likely be toxic or nutritionally useless to humans. The amino acids, sugars, and other basic biological building blocks might exist in forms our bodies couldn't process or might actively harm us. The sobering conclusion from exoplanet research is that truly Earth-like planets, those where humans could survive without massive technological intervention, are likely exceedingly rare. The few potentially habitable worlds we've identified would still require centuries of terraforming to approach Earth-like conditions, assuming such terraforming is even possible with any foreseeable technology. The romantic notion of finding another Earth waiting for human settlement has given way to the harsh reality that most exoplanets would kill unprotected humans within minutes of arrival. This shortage of habitable destinations creates a fundamental question. Why undertake the enormous costs and risks of interstellar travel when the destinations themselves offer environments far more hostile than even the most extreme locations on Earth? Even Antarctica, or the deepest ocean trenches, are more hospitable to human life than the surface of Mars, let alone distant exoplanets with unknown environments. The lack of viable destinations undermines the entire rationale for interstellar travel beyond scientific curiosity, a motivation unlikely to sustain the massive multi-generational investment such journeys would require. Given the inhospitable nature of potential destinations, any interstellar mission would need to bring along its own Earth-like environment, a self-contained bubble of habitability in the form of life support systems. Yet these systems themselves present perhaps the most technically challenging aspect of long-duration spaceflight, with fundamental limitations that may prove insurmountable over interstellar timescales. Life support for interstellar missions faces a qualitatively different challenge than the systems used on the International Space Station or even proposed for Mars missions. Current space life support relies heavily on regular resupply from Earth and has mission durations measured in months or years, not the decades or centuries interstellar travel would require. The fundamental problem is closure, creating a system that recycles air, water, food, and waste with near-perfect efficiency for decades without external inputs. Oxygen regeneration presents the first critical challenge. Humans consume approximately 800 grams of oxygen daily through respiration, converting it to carbon dioxide. On the International Space Station, This carbon dioxide is currently scrubbed using replaceable lithium hydroxide canisters or mechanical systems that eventually require replacement parts from Earth. More advanced systems use plants or algae to convert carbon dioxide back to oxygen through photosynthesis. But these biological systems introduce their own complexities and instabilities. The water cycle presents similar challenges. Each person uses approximately 2.5 litres of water daily for drinking and food preparation, plus additional amounts for hygiene. While water recycling from urine and humidity condensation can recover up to 95% in current systems, that small percentage of loss becomes catastrophic over decades. A 1% loss rate would deplete half the water supply in 69 years, for interstellar missions lasting centuries. Even a 0.1% loss rate would be unsustainable without enormous initial water reserves adding substantial mass to the spacecraft. Food production creates an even more complex challenge. Hydroponic or aeroponic systems can grow plants without soil, but require carefully controlled lighting, nutrients, and environmental conditions. These systems are energy intensive, require significant space, and are vulnerable to crop diseases or pests that could spread rapidly in a closed environment. A single crop failure in a finely balanced closed system could trigger a cascade of ecological problems throughout the life support system. The nutrient cycles for plant growth must be meticulously maintained, with nitrogen, phosphorus, potassium, and micronutrients carefully recovered from human waste and inedible plant matter. Any imbalance in these cycles, too much of one nutrient or too little of another, could crash the food production system. Current closed systems experiments like Biosphere 2 demonstrated how difficult maintaining these balances can be, with unexpected interactions leading to oxygen depletion and crop failures despite careful planning. Waste processing presents another formidable challenge. Human biological waste must be completely broken down and its components returned to the life support system without loss. Solid waste, including inedible plant parts, packaging materials, and worn-out equipment, must either be completely recycled or stored indefinitely. The accumulation of even small amounts of non-recyclable waste over decades would eventually overwhelm storage capacity. Trace contaminant control presents a particularly insidious problem for long-duration life support. Humans and materials continuously release small amounts of gases, particulates, and volatile organic compounds. In Earth's vast atmosphere, these dilute to harmless levels, but in a sealed spacecraft they accumulate. Some contaminants are difficult to filter and can reach harmful concentrations over time. The longer the mission duration, the more comprehensive the contaminant control system must be, adding complexity and potential failure points. Microbial management creates another layer of complexity. Humans carry trillions of microorganisms that are essential to our health. These microbial communities must remain balanced within the spacecraft ecosystem. Harmful microbes must be controlled without disrupting beneficial ones. Over decades, microbial evolution within the closed environment could potentially produce strains resistant to control methods or adapted to consume critical spacecraft materials. System reliability over decades introduces perhaps the most fundamental challenge. Every pump, filter, dot, sensor, control system, and biological component has a limited operational lifetime. Mechanical systems wear out, electronics degrade, and biological systems evolve or adapt in unexpected ways. Redundancy can mitigate some failure modes, but adds mass and complexity. The cascading effects of even small failures in interconnected life support systems can quickly become catastrophic in a closed environment with no possibility of external assistance. The energy requirements for maintaining life support add another layer to the already impossible energy equation of interstellar travel. Growing food with artificial lighting alone requires approximately 1,000 kilowatt-hours per kilogram of edible food, an enormous energy demand for a spacecraft that must generate all its power independently for decades. Water purification, air circulation, temperature control, and waste processing all add to this substantial energy burden. Perhaps most fundamentally, the complexity of recreating Earth's life support systems, which rely on vast, interconnected ecosystems with millions of species in a spacecraft environment, may represent a problem of irreducible complexity. Earth's biosphere maintains its stability through enormous redundancy and diversity that cannot be fully replicated at spacecraft scales. The simplified ecosystems possible within a spacecraft lack the resilience and self-correcting properties of Earth's vastly more complex systems. The history of closed ecological system experiments on Earth does not inspire confidence. Biosphere 2, the most ambitious closed system experiment to date, encountered numerous unforeseen problems, including oxygen depletion, nutrient imbalances, and unexpected species interactions despite having the advantages of Earth's gravity, sunlight, and the possibility of external intervention if needed. Scaling up such systems to operate reliably for decades without any possibility of outside assistance or intervention remains well beyond our current capabilities and possibly beyond what can be achieved even in principle. The inherent complexity of life support systems reveals another layer of the interstellar challenge. Even if we could somehow create a perfectly functioning closed ecosystem within a spacecraft, the vessel would still be fundamentally isolated in the most extreme sense humanity has ever experienced. The problem of interstellar communication creates a disconnect more profound than any faced by previous explorers, with implications that undermine the entire concept of coordinated interstellar missions. Communication across interstellar distances is governed by the same light speed limit that constrains physical travel. Radio waves, laser beams, and all other forms of electromagnetic communication travel at exactly the same speed as light, approximately 670 million miles per hour. This creates an inescapable time delay for any attempt to communicate between star systems. A message sent to even the nearest star system, Alpha Centauri dot, would take 4.3 years to arrive, and another 4.3 years for a reply to return to Earth. For star systems 20 or 30 light years away, where most potentially interesting exoplanets have been discovered, the round-trip communication time extends to 40 or 60 years. These delays render conventional conversation impossible. Consider how this would affect an interstellar mission. If the crew encountered a serious problem requiring Earth's assistance, they would have to wait years or decades for a response to their distress signal. By then, the situation would have either resolved itself, likely catastrophically, or evolved into an entirely different problem. The notion of mission control providing real-time guidance, as happens with current space missions, becomes completely untenable across interstellar distances. The communication delay also creates profound coordination problems. Any instructions sent from Earth would be based on ship conditions that existed years earlier. The mission planners would be perpetually giving outdated instructions to address situations that have long since changed. Imagine trying to remotely perform complex spacecraft maintenance when your instructions are based on conditions that existed a decade ago, and you begin to appreciate the coordination impossibility. Beyond the delay problem lies the signal strength challenge. Radio signals weaken according to the inverse square law, double the distance, and the signal becomes 4 times weaker. By the time radio transmissions reach interstellar distances, they become incredibly faint, difficult to distinguish from the background noise of space. Our most powerful current transmitters would produce signals barely detectable by our most sensitive receivers at distances of just a few light years, even with huge receiving antennas. To overcome this signal attenuation, interstellar communications would require enormously powerful transmitters, large-scale receiving antennas, or highly focused laser communication systems. All these solutions demand tremendous energy expenditure precisely when energy would be at its greatest premium aboard an interstellar vessel. The energy required to maintain reliable communications across light years might constitute a significant portion of the spacecraft's entire energy budget. further straining the already impossible energy equation of interstellar travel. Data transmission rates present another limiting factor. Current deep space missions like the New Horizons probe communicate at data rates measured in kilobits per second, roughly comparable to 1990s dial-up internet. Scaling this to interstellar distances would reduce data rates to mere bits per second or less, making the transmission of detailed scientific data, let alone rich media like images or video, painfully slow. Sending a single high-resolution image might take months, while video communication would be practically impossible. The reliability of communications over decades or centuries introduces yet another layer of complexity. Any communication system has an inherent bit error rate, the percentage of transmitted bits that are received incorrectly. Over interstellar distances, cosmic radiation and signal attenuation would significantly increase these error rates. Error correction coding can help but requires sending redundant data, further reducing already constrained bandwidth. Over decades-long missions, the cumulative effect of these error rates could render significant portions of transmitted data unusable. The communication systems themselves would also degrade over time. Transmitter components wear out, electronic systems experience radiation damage, and calibration drifts. With no possibility of physical repairs or replacements from Earth, redundant systems would be essential, adding mass and complexity to the spacecraft. The failure of primary communication systems could leave a mission completely isolated, with no way to report findings or receive guidance. Perhaps most fundamentally, the content of interstellar communications would face a cultural and contextual gap that widens with time. Language evolves rapidly. The English of 400 years ago is barely comprehensible to modern speakers. Scientific terminology, cultural references, and technological contexts shift dramatically over decades. After a century of separation, the crew of an interstellar mission might struggle to understand communications from an Earth culture that had evolved in their absence. Similarly, Earth-based mission controllers might struggle to interpret messages from a crew whose isolated culture had diverged significantly from Earth norms. The one-way nature of deep space communication creates a psychological barrier as well. Astronauts on current missions know they're in constant contact with Earth, with real-time or near real-time communication providing a psychological lifeline. Interstellar travelers would face a profound isolation unlike anything in human experience. Messages would be essentially missives from the distant past rather than ongoing conversations. This communication gulf would likely contribute to the cultural divergence between ship and Earth, further complicating the mission's connection to its origin. Advances in artificial intelligence are sometimes proposed as a solution, with AI systems standing in for human mission controllers to provide immediate guidance. However, this merely transforms the communication problem into an AI capability problem. No AI system could anticipate all possible contingencies an interstellar mission might face, and any AI capable of truly independent decision-making would face its own divergence issues as it evolved separately from Earth-based systems over decades. The communication barrier creates a fundamental paradox for interstellar exploration. The further we send our explorers, the less connection they maintain with the civilization that sent them. At some point, the delay and difficulty become so severe that the mission effectively becomes an independent entity, disconnected from Earth in any meaningful sense. This raises profound questions about the purpose of sending human explorers rather than autonomous probes, when those humans would be effectively cut off from the civilization they represent. The communication challenges of interstellar travel reveal a sobering truth. Any human interstellar mission would be functionally on its own, unable to receive meaningful assistance or guidance from Earth. This level of isolation requires a degree of mission autonomy and self-sufficiency far beyond anything attempted in the history of exploration, further undermining the feasibility of crewed interstellar travel. The profound isolation imposed by interstellar communication barriers points to yet another fundamental obstacle. The political impossibility of sustaining multi-generational projects. Even if we could somehow overcome the technical challenges of interstellar travel, the political and social structures of human civilization appear fundamentally incompatible with the timescales such projects would require. Consider that the longest continuously operated human-made structure, the Great Wall of China, took approximately 2,000 years to build in its current form, spanning dozens of dynasties, revolutions, and complete governmental collapses. Yet even this project, visible from space, was repeatedly abandoned, repurposed, and rebuilt as political priorities shifted. Now imagine attempting to maintain political commitment to an interstellar program that might not yield results for centuries, far longer than any government in human history has maintained continuous policy on any subject. Modern democratic systems operate on election cycles of 2 to 6 years, with major policy reversals possible with each change in leadership. Even the most ambitious space programs struggle to maintain consistent funding and direction across multiple administrations. The Apollo program, perhaps the most focused space effort in history, lasted only about a decade before budget cuts and changing priorities ended lunar exploration. More recently, NASA has seen Mars mission architectures completely redesigned with each new administration, preventing sustained progress toward even this much more modest goal. The International Space Station, our most successful international space collaboration, has required constant diplomatic reinforcement to maintain funding commitments across its lifetime. Even with 16 participating nations and hundreds of billions of dollars invested, its continued operation remains subject to regular funding reviews and political uncertainty. Scaling this model to interstellar missions lasting centuries seems politically unfeasible. Authoritarian regimes fare no better at long-term project maintenance. While dictatorships can sometimes mobilize resources more decisively in the short term, they show even less stability over decades. The Soviet space program achieved early successes but ultimately lost momentum as leadership changed and economic realities shifted. China's space program has shown impressive recent progress but remains subject to the same potential for policy reversal with leadership transitions. The economic commitment required for interstellar projects would inevitably compete with immediate human needs: healthcare, education, infrastructure, environmental protection, creating constant political pressure to redirect resources to more immediate concerns. Democratic systems are particularly responsive to constituent demands for addressing current problems rather than investing in speculative long-term projects. In times of economic hardship, space programs are typically among the first budget items to face cuts. Historical precedent for multi-generational projects is not encouraging. Medieval cathedrals often took over a century to build, but frequently saw designs altered midway, funding interrupted, or construction abandoned as priorities shifted. The modern era, with its accelerated pace of technological and social change, shows even less ability to maintain consistent direction on long-term projects. Programs lasting more than a decade frequently become technological anachronisms before completion, as the underlying assumptions and technologies become obsolete. Even within the space community itself, maintaining consistent priorities has proven challenging. The vision for space exploration announced in 2004 was substantially revised by 2010. The James Webb Space Telescope, while eventually successful, faced numerous cancellation attempts during its long development. These examples involve timeframes of merely years or decades. Scaling to the centuries required for interstellar missions magnifies the consistency problem exponentially. The intergenerational commitment problem extends beyond governments to public support. Public enthusiasm for space exploration tends to surge with major achievements but wanes during the long development periods between milestones. Maintaining taxpayer support for projects whose benefits might not be realized for centuries presents an arguably impossible public relations challenge. Future generations, having no say in the initial commitment of resources, might reasonably question or reject the decisions made by their ancestors to allocate substantial resources to such long-term speculative ventures. International competition further complicates long-term space commitments. The Cold War space race produced rapid progress but was driven by geopolitical competition rather than sustainable scientific goals. Today's multipolar world, with competing space powers like the United States, China, Russia, and Europe, creates a complex environment where unilateral long-term commitments seem unlikely, while truly global cooperation remains elusive. The fragility of international agreements, which can be abandoned when national priorities change, makes them poor foundations for century-spanning projects. Corporate involvement, sometimes suggested as an alternative to governmental programs, introduces its own temporal limitations. Public corporations operate on quarterly reporting cycles, with strategic plans rarely extending beyond 5 years. Even the most visionary corporate leaders must ultimately answer to shareholders or boards focused on near-term returns. The longest-lived corporations in history have survived for a few centuries at most, often transforming their core business multiple times, hardly the stability required for interstellar programs spanning similar timeframes. Perhaps most fundamentally, human political systems evolved to address immediate and near-term challenges faced by small groups. Our psychology and social structures aren't adapted for thinking or planning across centuries. We struggle to make political commitments even to address climate change, whose worst effects might manifest within decades. Extending this to projects with payoffs centuries away seems to ask for a type of political foresight and commitment that human social structures have never demonstrated. The political discontinuity problem creates a paradoxical situation. The longer and more ambitious the space mission, the less likely it is to maintain the sustained political support needed for completion. Interstellar missions represent the extreme case of this paradox, requiring political continuity over timeframes that exceed the demonstrated stability of any human political system in history. This political impossibility may represent an even more fundamental barrier than the technical challenges, as it suggests that even if we could theoretically build interstellar vessels, human civilization may be structurally incapable of sustaining the effort required to actually do so. The political instability of human institutions reveals a deeper barrier to interstellar travel: our minds themselves. While we often imagine technological solutions to physical challenges, the evolutionary constraints of human psychology present obstacles that may be even more fundamental. Our brains didn't evolve for space travel, they evolved specifically for life on Earth, with psychological adaptations that become serious liabilities during long-duration missions beyond our home planet. Consider first our evolved need for natural environments. Humans evolved in settings with open skies, natural landscapes, diverse ecosystems, and day-night cycles synchronized with our home planet. These aren't merely preferences, but deep-seated psychological requirements. Studies consistently show that exposure to natural environments reduces stress, improves cognitive function, and supports mental health. Even brief deprivation of these natural settings causes measurable psychological distress. The concept of nature deficit disorder, while not a formal diagnosis, describes the documented negative effects when humans lack access to natural environments. These effects include increased anxiety, depression, attention problems, and stress-related disorders. Now imagine not a temporary deprivation of nature, but a permanent one, living your entire life inside an artificial habitat with no possibility of ever experiencing an open sky, natural weather, or unregulated ecosystems. The psychological toll would be enormous and cumulative. Space psychology research from orbital missions already demonstrates concerning patterns. Even highly trained astronauts experience cognitive changes, sleep disruption, mood disorders, and interpersonal conflicts during missions lasting mere months. These effects occur despite knowing they'll soon return to Earth. Interstellar crews would face these same stressors without the psychological relief of an upcoming homecoming, creating conditions for severe long-term mental health deterioration. Our spatial psychology presents another constraint. Humans have evolved a specific response to environments based on certain spatial parameters: ceiling heights, sight lines, and escape routes. Confined environments trigger subtle but persistent stress responses in most people. The proxemics of interstellar vessels, the necessarily confined spaces where privacy would be limited and personal territory constantly negotiated, run contrary to deep psychological needs for personal space and territory. Social psychology presents perhaps an even more fundamental barrier. Human social structures evolved for specific group sizes, from immediate family units to tribes of roughly 150 individuals, known as Dunbar's number. This represents the approximate maximum number of meaningful social relationships our brains evolved to manage. Generationships would likely need larger populations to maintain genetic diversity, forcing social structures that exceed our evolved capabilities. Alternatively, smaller populations would face extreme social stagnation with too few potential relationship combinations to satisfy human social needs over decades. Temporal psychology, how we perceive and value time, creates another mismatch. Human motivation systems evolved to prioritize relatively immediate rewards over distant ones, a phenomenon psychologists call temporal discounting. We struggle to maintain motivation for goals weeks or months away, let alone decades. This made perfect evolutionary sense. Our ancestors needed to prioritize immediate survival over speculative long-term projects. But this same psychology makes maintaining motivation for century-long missions nearly impossible. Our reward systems are similarly mismatched to interstellar timescales. The dopamine-driven reward circuits in our brains evolved to reinforce behaviors that produced relatively quick results. These systems struggle to maintain motivation for projects without periodic rewarding milestones. Interstellar travel offers few such milestones, just the endless void of space for potentially decades before reaching any destination. The reward drought during transit would likely trigger motivation collapse, depression, and potentially mission abandonment. Then there's our evolved psychology around meaning and purpose. Humans need to feel their actions contribute to something larger than themselves, a need typically met through visible impact on community, creation of lasting works, or contribution to family lineage. Interstellar travelers would be severed from these traditional sources of meaning. Their actions would benefit unknown future generations rather than anyone they could directly observe, creating a meaning deficit difficult to overcome psychologically. Our risk assessment capabilities present another evolved limitation. Human brains evolved to evaluate familiar risks, predators, hostile tribes, natural disasters. We struggle to accurately assess novel or statistical risks, consistently overestimating dramatic but rare dangers while underestimating chronic, cumulative threats. The risk landscape of interstellar travel, radiation exposure, equipment failure, psychological deterioration, consists precisely of the types of statistical, cumulative risks our brains are worst at evaluating and responding to appropriately. Information processing limitations create additional barriers. Our attentional systems evolved for environments with high stimulus diversity, changing landscapes, weather patterns, plant and animal behaviors. In the sensory monotony of spacecraft interiors, attention systems deteriorate, leading to vigilance decrements, boredom, and increased error rates in critical tasks. The lack of novel stimuli over years would likely cause serious cognitive impairments in even the most disciplined crews. Perhaps most fundamentally, our brains evolved under Earth-specific conditions, its gravity, atmospheric pressure, magnetic field, solar radiation levels, and countless other parameters. Emerging research suggests these conditions affect everything from fluid dynamics in the brain to neurochemical processes. The long-term neural consequences of living in artificial environments with different gravitational conditions remain largely unknown, but potentially severe. The multi-generational aspect of interstellar travel introduces additional psychological complications. Children born on generation ships would have no direct experience of Earth, no evolutionary context for their psychological needs, and no connection to the mission's original purpose. Their psychological development would occur in an environment radically different from the one our species evolved for, with unpredictable consequences for their mental health, cognitive development, and social adjustment. While some suggest genetic engineering or neural implants might modify human psychology to better suit space travel, such approaches face both technical and ethical barriers. Our understanding of the genetic basis for complex psychological traits remains rudimentary, and the interconnected nature of neural systems means modifications targeting specific traits would likely have unpredictable effects on other aspects of cognition and emotion. The brain isn't a machine with discrete, independently modifiable modules, but an integrated system shaped by millions of years of evolution specifically for terrestrial life. These psychological constraints aren't merely challenges to be overcome through better spacecraft design or crew selection. They represent fundamental mismatches between the environment our minds evolved for and the conditions of interstellar travel, just as our bodies face biological barriers to space travel. Our minds face psychological ones that may be equally insurmountable. The human brain, exquisitely adapted for life on Earth, may simply be incompatible with the conditions necessary for interstellar journeys. Beyond the constraints of human psychology lies another formidable barrier to interstellar travel. The sheer material requirements for building interstellar spacecraft would likely exceed Earth's available resources, creating an insurmountable resource depletion barrier. When we calculate the materials needed for viable interstellar missions, we confront the stark reality of our planet's finite supplies. Consider the basic materials required for spacecraft construction. A generation ship capable of supporting even a small population of 1,000 people for centuries would require a structure orders of magnitude greater than larger than the International Space Station. Conservative estimates suggest such vessels would need millions of tons of materials: high-grade aluminum, titanium, steel, carbon composites, radiation shielding materials, and countless specialized components. Titanium, essential for spacecraft construction due to its strength-to-weight ratio and temperature resistance, is already facing supply constraints for terrestrial applications. Global reserves of economically extractable titanium are estimated at about 750 million tons, seemingly abundant until you consider the massive quantities required for even a small fleet of interstellar vessels. Plus, competing demands from aircraft, military applications, and consumer products. Rare earth elements present an even more severe constraint. These 17 elements are crucial for electronics, motors, batteries, and countless other advanced technologies. Current global reserves of many rare earths may be depleted within decades at current consumption rates, even without the enormous additional demand interstellar projects would create. Elements like neodymium, used in powerful magnets for motors and generators, or yttrium, used in laser technologies and radiation-resistant materials, face particularly severe supply constraints. Helium-3, often proposed as an ideal fuel for advanced fusion propulsion systems, is extremely rare on Earth. The total accessible supply would be insufficient for even a single major interstellar mission, while helium-3 is more abundant on the Moon. Extracting it would require massive lunar mining operations, themselves demanding enormous material resources and energy. The radiation shielding requirements alone present a daunting resource challenge. Effective cosmic radiation protection requires thick layers of hydrogen-rich materials or heavy elements like lead. The quantities required for protecting a generation ship's habitat for centuries would likely exceed tens of thousands of tons per vessel, a substantial fraction of annual global production for some of these materials. Many point to asteroid mining as the solution to these resource limitations. In theory, a single metal-rich asteroid could contain more platinum group metals than have been mined throughout human history. However, the infrastructure required to establish effective asteroid mining operations would itself demand enormous resources. We would need to build fleets of specialized spacecraft, processing facilities in orbit, and transportation systems to move materials, all before extracting the first gram of useful material for our interstellar vessels. The energy requirements for resource extraction and processing compound the problem. Mining operations on Earth already consume approximately 10% of global energy production. Extending mining to space would require far higher energy inputs per unit of material extracted due to the challenges of operating in vacuum, microgravity, and radiation environments. This energy would need to come from somewhere, likely requiring yet more resource-intensive infrastructure like space-based solar arrays or nuclear facilities. Even if we could somehow extract sufficient raw materials, the manufacturing capacity required to transform them into interstellar vessels exceeds anything humanity has built. Consider that the largest shipyards on Earth, after centuries of industrial development, can produce ocean vessels of a few 100,000 tons. An interstellar generation ship would likely need to be many times larger, with far more complex systems. Building even one such vessel would require manufacturing capabilities far beyond our current global capacity. The precision components needed for advanced propulsion, life support, and computing systems introduce additional resource constraints. Many require extremely pure materials, exotic alloys, or specialized manufacturing processes that themselves consume significant resources. The semiconductor industry, for instance, relies on extraordinarily pure silicon and numerous rare elements, with supply chains already showing strain for meeting terrestrial technology needs. The resource problem becomes circular. To gather the resources needed for interstellar travel, we would first need to develop extensive space-based infrastructure, which itself would require enormous resources to build. This chicken and egg problem creates a bootstrapping barrier that may be fundamentally insurmountable given Earth's finite resource base. Recycling offers only partial mitigation. Even the most advanced recycling technologies cannot achieve 100% efficiency. Material degradation, contamination, and fundamental thermodynamic limitations mean some percentage of critical materials is lost with each recycling cycle, over decades or centuries. These losses would become significant without new inputs, precisely the situation an interstellar mission would face. The competition for these same limited resources from terrestrial needs creates an allocation dilemma. As Earth's population grows and developing nations industrialize, demand for key materials continues to increase. Critical resources like copper, zinc, gold, and many rare earth elements already face potential supply constraints within this century. Even without adding the enormous demands of interstellar projects, water presents another resource challenge often overlooked. A self-contained habitat for 1,000 people would need to carry hundreds of thousands of tons of water for drinking, food production, and technical systems. While water can be recycled, achieving the near-perfect efficiency needed for centuries-long missions remains beyond current technology. The mass of water alone would make interstellar vessels enormously heavy, further exacerbating propulsion energy requirements. The industrial ecology of spacecraft construction introduces yet another layer of resource requirements. Modern manufacturing relies on global supply chains involving thousands of specialized facilities, each producing specific components that ultimately come together in finished products. Replicating this entire industrial base for spacecraft construction would require not just raw materials, but an unprecedented concentration of diverse manufacturing capabilities, itself resource-intensive to develop and maintain. Perhaps most fundamentally, the resources needed for interstellar travel would need to be diverted from addressing immediate human needs and existing environmental challenges. As climate change, biodiversity loss, and resource depletion already strain Earth's carrying capacity. Allocating vast resources to speculative interstellar ventures becomes increasingly difficult to justify ethically. Clean water, sustainable agriculture, renewable energy, and habitat preservation all compete for the same finite resources interstellar projects would require. This resource constraint isn't merely a temporary limitation of current technology or economic systems. It represents a fundamental mismatch between the material requirements of interstellar travel and the finite resource base available to a planetary civilization. The laws of physics and chemistry place absolute limits on material availability that no social system or technological advance can overcome. We cannot manufacture elements that don't exist or extract resources in quantities that exceed planetary reserves. This resource barrier may ultimately prove even more limiting than the technical challenges of propulsion or life support, forcing humanity to accept that our ambitions for the stars may simply exceed what our home planet can provide. The finite resource constraints of our planet highlight another sobering reality that undermines interstellar ambitions: the inevitability of technological regression over long time periods. While we often imagine technological development as a continuously upward trajectory, historical evidence reveals a far more complex pattern of advancement, stagnation, and periodic collapse that poses a fundamental challenge to projects spanning centuries. Human technological history doesn't show steady, uninterrupted progress. Instead, we see periods of rapid innovation followed by plateaus or even dramatic reversals. The collapse of the Roman Empire led to the loss of numerous technologies, from advanced concrete formulas to sophisticated hydraulic systems that took centuries or even millennia to rediscover. The Bronze Age collapse around 1200 BCE caused writing systems to disappear and sophisticated metallurgical knowledge to be lost across multiple civilizations. These weren't minor setbacks, but catastrophic losses of crucial technical capabilities. Modern technology faces similar vulnerability, but with greater potential consequences due to its increased complexity. Today's advanced systems, from semiconductor manufacturing to genetic engineering, require vastly specialized knowledge distributed across thousands of experts, none of whom possess complete understanding of entire systems. This distributed expertise creates dangerous fragility, as knowledge can be lost during societal disruptions when specialists die without adequately transmitting their understanding to the next generation. The semiconductor industry illustrates this vulnerability perfectly. Manufacturing modern microprocessors requires hundreds of precisely sequenced steps, specialized materials, and equipment so complex that only a handful of companies worldwide can produce the most advanced chips. This knowledge is not fully documented in any single source, but exists partially in the accumulated expertise of thousands of engineers and technicians. Even a relatively brief disruption in this field could set back computing technology by decades if key personnel or facilities were lost. Interstellar programs would require not just maintaining our current technology, but continuously advancing it over centuries. Yet history shows even maintaining existing technology requires uninterrupted chains of knowledge transmission. During the early Middle Ages, techniques for making structures like the Roman Pantheon's dome were lost for nearly 1,000 years despite their obvious utility. The technical sophistication needed for interstellar travel, orders of magnitude beyond our current capabilities, would be even more vulnerable to such knowledge discontinuities. The interdependence of modern technological systems creates additional fragility. Advanced technology forms complex webs where critical components rely on other specialized technologies for their production. Computer chip manufacturing requires precisely controlled chemicals, which require specialized production facilities, which require specific catalysts, which require particular mining techniques, creating chains of dependency dozens of layers deep. Disruption at any point can cascade through the entire system. An interstellar program would need to maintain all these interdependent technologies simultaneously over centuries without significant interruption. This technological interdependence creates single points of failure that didn't exist in less advanced societies. when specialized knowledge or production capacity exists in only a few locations. Its loss can trigger widespread technological regression. Historical examples like the Library of Alexandria demonstrate how concentrated knowledge can be permanently lost. But modern technology has created far more numerous and critical choke points where failure would be catastrophic. Resource competition during crises inevitably prioritizes immediate survival technologies over speculative long-term projects. During economic downturns, funding for advanced research is typically cut first. In more severe crises like wars or natural disasters, industrial capacity is redirected toward immediate needs. The massive resource requirements of interstellar programs would make them particularly vulnerable to reprioritization during inevitable periods of resource scarcity or social stress. The specialized nature of space technology makes it especially vulnerable to regression. Unlike technologies with broad consumer applications that create incentives for continuous investment, space capabilities often serve narrow purposes with limited commercial potential. When NASA's Apollo program ended, the United States actually lost the capability to send humans to the moon, a technology regression that has lasted half a century and counting. If we can lose such capability after just a few decades, maintaining the far more advanced technology for interstellar travel over centuries seems highly improbable. Energy system disruptions pose another regression risk. Advanced technology requires stable, abundant energy supplies. Historical energy transitions, from wood to coal to oil to potential renewables, have never been smooth, often involving supply disruptions and price volatility. Any serious energy supply disruption during a centuries-long interstellar program development would likely cause irreversible setbacks as research facilities shut down, manufacturing capabilities are lost, and expertise dissipates. Climate instability presents yet another regression threat. As climate change accelerates, unpredictable disruptions to agriculture, water supplies, coastal infrastructure, and population distributions become increasingly likely. Such disruptions historically correlate strongly with technological regression as societies redirect resources toward basic adaptation rather than advanced technology development. The coming centuries, precisely when interstellar technology would need to be developed, may see unprecedented climate instability that triggers technological regression rather than advancement. Perhaps most fundamentally, technological progress requires stable social institutions. Universities, research laboratories, corporations, and government agencies must maintain consistent funding, purpose, and organizational memory. Yet these institutions have historically proven fragile during social disruptions. The average lifespan of a corporation is under 20 years. Universities have shown greater longevity but still undergo periodic reforms that change their research priorities and institutional knowledge. The institutional stability required for century-spanning technological development has simply never existed in human history. The historical evidence suggests that maintaining continuous technological advancement over centuries, let alone the accelerated advancement needed to achieve interstellar capability, is profoundly unlikely given the inevitable disruptions human civilization will face. The technology needed for interstellar travel isn't just slightly beyond our current capabilities. It requires multiple revolutionary breakthroughs sustained over generations without significant regression, a pattern with no historical precedent. The technological regression threat reveals that interstellar travel isn't merely a matter of eventually accumulating sufficient technological advancement. Instead, it requires a kind of social and technological continuity that human civilization has never achieved and shows little indication of being capable of maintaining over the necessary timeframes. While technological regression threatens the long-term development of interstellar capabilities, an equally challenging obstacle emerges within the social dynamics of any interstellar mission itself. The social cohesion paradox represents another fundamental barrier that undermines the feasibility of crewed interstellar travel, particularly for the generation ship model often proposed as a solution to the distance problem. Human groups confined to isolated environments for extended periods inevitably develop problematic social dynamics that threaten mission viability. This isn't speculative, it's supported by extensive evidence from isolated human communities throughout history and from formal isolation studies. Submarines, Antarctic research stations, biosphere experiments, and space station missions all demonstrate consistent patterns of social deterioration over time, despite involving highly selected, well-trained personnel with strong initial commitment to mission objectives. The classic BIOS 3 experiment in Russia, where 3 people lived in a sealed environment for 6 months, resulted in such severe interpersonal conflicts that some participants stopped speaking to each other entirely. The Mars Society's Mars Desert Research Station regularly reports significant interpersonal tensions during missions lasting just weeks. Even the International Space Station, with highly trained astronauts on relatively short rotations, experiences interpersonal conflicts that require careful management from ground support, a luxury unavailable to truly isolated interstellar travelers. Small group psychology reveals fundamental problems that emerge in isolated communities. Groups under stress naturally form coalitions and factions, with individuals competing for status, resources, and influence. In terrestrial societies, dissatisfied individuals can leave groups that become dysfunctional. In the closed environment of an interstellar spacecraft, this escape valve doesn't exist, intensifying conflicts and allowing toxic social dynamics to escalate without resolution. The social environment aboard a generation ship would likely develop extreme stratification and inequality. Historical isolated communities like oceanic island populations or remote religious communes frequently developed rigid social hierarchies with privileged elites controlling resources and opportunities. On a generation ship, such stratification could become severe, with certain groups monopolizing crucial resources, educational opportunities, or desirable living spaces. This stratification creates resentment and potential for conflict that could ultimately threaten mission viability. Sexual and reproductive dynamics present particularly volatile social challenges. Within a small, isolated population, partner selection becomes extremely limited. Jealousy, competition for mates, and conflicts over reproductive rights have historically caused severe disruptions in isolated communities. The necessity of managing genetic diversity would require some form of reproductive regulation, creating further potential for resentment and resistance. Historical communes that attempted to regulate reproduction often collapsed, specifically due to conflicts arising from these regulations. Generational differences would create another layer of social instability. The first generation, those who chose to embark on the mission, would have fundamentally different perspectives than subsequent generations born into the ship environment. These later generations, having never experienced Earth or chosen the mission, would likely question or reject the priorities, values, and authority structures established by the founding generation. This generational divergence creates potential for fundamental conflict about the mission's purpose and governance. Authority and governance pose particularly difficult challenges. Maintaining order in isolated environments typically requires either strong authoritarian control or robust democratic institutions, both systems facing severe problems over multi-generational timeframes. Authoritarian systems tend toward abuse and eventually face resistance or revolution. Democratic systems can be undermined by factionalism and popularity-driven decision-making that might prioritize short-term satisfaction over long-term mission requirements. Neither system has demonstrated stability over the century-plus timescales interstellar missions would require. Cultural divergence compounds these governance challenges. Human cultures naturally drift and evolve, with new values, beliefs, and practices emerging over generations. This cultural evolution occurs more rapidly in isolated populations, within just a few generations. The culture aboard a generation ship would likely diverge dramatically from both Earth culture and the founding mission culture. This divergence could easily produce value systems incompatible with continuing the original mission objectives. Religious and ideological transformations frequently emerge in isolated communities, sometimes taking extreme forms. New belief systems could arise that actively oppose the mission's original purpose, or create divisions between believers and non-believers. Historical examples like the Pitcairn Islanders, descendants of the Bounty Mutineers, or various isolated religious communes, demonstrate how quickly isolated populations can develop radically transformed belief systems that would be completely unpredictable to mission planners. The children raised in such environments would experience profound psychological and developmental differences from Earth-raised humans. Without exposure to diverse social groups, natural environments, or the cultural context that shaped the mission, their conceptual frameworks would diverge dramatically from those of the founding generation. Their understanding of concepts like Earth, moral mission, or even humanity would be based entirely on second-hand information, creating a kind of cultural and conceptual disconnect that would widen with each succeeding generation. Perhaps most fundamentally, the motivation maintaining the mission would inevitably deteriorate over generations. The founding crew might accept hardship for a goal they personally value. Their children, raised with stories of Earth and the mission's importance, might maintain some commitment, but their grandchildren and subsequent generations would have increasingly tenuous connection to these original motivations. Why should they maintain difficult protocols, accept resource limitations, or perform demanding maintenance tasks for a mission they never chose, serving the interests of distant descendants they'll never meet? Historical evidence from isolated communities suggests that within 3 to 4 generations, the original mission values would likely be substantially abandoned or transformed beyond recognition. Without the option to enforce compliance from outside, an impossibility for truly interstellar missions, there's no mechanism to prevent later generations from simply abandoning or radically redefining the mission to serve their immediate perceived needs rather than the original intergenerational objective. This social cohesion paradox reveals that the human social fabric itself may be fundamentally incompatible with the multi-generational cooperation required for interstellar travel. We cannot simply engineer around this problem with better ship design or crew selection because it emerges from core aspects of human social psychology that evolved specifically for life in open, Earth-bound communities with the option of mobility and group reconfiguration. The social requirements of successful interstellar travel may be as unachievable as faster-than-light propulsion, not merely technically challenging but fundamentally incompatible with human nature itself. The human social dynamics that would inevitably undermine generational missions reveal an even more fundamental issue: the profound ethical problems inherent to interstellar colonization attempts. While discussions about interstellar travel often focus on technical and scientific challenges, the ethical barriers may ultimately prove the most insurmountable of all. These ethical concerns aren't merely philosophical abstractions, but concrete problems that any advanced civilization would need to confront before launching such missions. The most fundamental ethical problem centers on consent. The first generation aboard an interstellar vessel might volunteer with full understanding of the hardships involved. However, all subsequent generations, potentially dozens or hundreds over the course of a journey, would never have the opportunity to consent to their circumstances. They would be born into what amounts to a prison with no possibility of escape, their entire lives predetermined by decisions made before their birth. This lack of consent represents an extraordinary violation of human autonomy. In essentially all other contexts, we recognize that confining humans to restricted environments without their consent constitutes a severe rights violation. We generally consider it acceptable only as punishment for serious crimes or in very limited medical circumstances with strict oversight. Yet interstellar missions would impose such confinement on countless individuals whose only crime was being born aboard the vessel. Children born on generation ships would face profoundly limited options compared to Earth-born humans. Their career choices, living arrangements, reproductive options, and even basic freedoms would be severely constrained by the mission requirements and limited resources. They could never choose to leave the mission or pursue life paths incompatible with spacecraft operations. This restriction of fundamental human freedoms raises serious questions about whether such missions could ever be ethically justified. The psychological impact on these non-consenting generations would likely be severe. Knowing that your entire existence is merely instrumental, a link in a chain designed to benefit some future generation that might reach the destination, could create profound existential distress. This instrumentalization of human lives, treating people as means rather than ends in themselves, violates basic principles of human dignity recognized in virtually all ethical frameworks. Beyond the consent problem lies the issue of risk transfer. The initiators of interstellar missions would be imposing extraordinary risks on future generations who had no say in accepting those risks. These include radiation exposure, equipment failure, resource depletion, social collapse, and countless other hazards. Ethical risk management typically requires that those who might benefit from an activity should be the ones bearing its risks. Interstellar missions fundamentally invert this principle, with the risk-takers never seeing the potential benefits. The resource allocation ethics present another serious barrier. The enormous resources required for interstellar missions would necessarily be diverted from addressing immediate human needs on Earth. While current space programs constitute a tiny fraction of global spending, true interstellar capabilities would demand resources orders of magnitude greater. Diverting such resources while problems like poverty, disease, environmental degradation, and social inequality remain unsolved raises profound questions about moral priorities. Can we justify spending trillions to send a tiny fraction of humanity to another star while billions suffer from addressable problems on Earth? The potential for biological contamination creates bidirectional ethical concerns. Human microbes could devastate alien ecosystems, potentially causing extinction events on worlds with existing life. Conversely, alien microorganisms could prove deadly to human colonists or, if brought back to Earth, trigger devastating pandemics. The risk of becoming unwitting agents of ecological disaster, potentially eliminating unique evolutionary developments billions of years in the making, creates a moral burden that cannot be easily dismissed. The genetic engineering likely necessary for adapting humans to long-duration space missions or alien environments raises its own ethical red flags. Modifying human genetics to withstand radiation, reduce resource requirements, or function in different gravity conditions would fundamentally alter what it means to be human. Making such permanent, heritable changes, especially without the consent of future generations who would carry these modifications, crosses significant ethical boundaries around human dignity and self-determination. The potential for technological abandonment presents another ethical dimension rarely discussed. If faster technology were developed after a slower ship had launched, the earlier mission's crew might arrive at their destination only to find it already colonized by humans who departed Earth centuries later but arrived earlier due to better propulsion. This scenario would render the entire multi-generational sacrifice of the earlier crew meaningless, an outcome that would be not merely tragic but ethically indefensible in terms of wasted human lives. The irreversibility of interstellar missions compounds all these ethical concerns. Unlike most human endeavours where mistakes can be corrected and courses adjusted, launching humans on a one-way interstellar journey creates a situation where ethical misjudgments cannot be remedied. If conditions aboard become unbearable, if resources run short, or if social structures collapse, there would be no possibility of rescue or return. This irreversibility demands an extraordinary ethical certainty that such missions would succeed, a certainty that seems impossible given the countless unknowns involved. Perhaps most fundamentally, interstellar colonization may represent a profound failure of intergenerational ethics. prioritizing an uncertain future for a tiny fraction of humanity over addressing solvable problems affecting billions in the present and near future. The moral mathematics simply doesn't add up when we consider the certain suffering that could be alleviated with the same resources that might send a few hundred humans toward an uncertain fate among the stars. These ethical barriers aren't merely temporary obstacles that future societies might casually dismiss. They reflect fundamental principles about human autonomy, consent, dignity, and the fair distribution of benefits and burdens. Any civilization advanced enough to develop interstellar capabilities would likely also have developed ethical frameworks sophisticated enough to recognize these problems. This suggests that the absence of interstellar civilizations might reflect not just technological limitations but ethical choices, conscious decisions that such missions cannot be justified given their profound moral costs. Faced with these ethical dilemmas surrounding human interstellar travel, many proponents suggest artificial intelligence as an alternative approach. Why not send sophisticated AI systems or robotic probes instead of fragile humans? These wouldn't face the same biological vulnerabilities or ethical concerns regarding consent and confinement. However, examining the fundamental limitations of artificial intelligence for long-duration space missions reveals new layers of insurmountable challenges that undermine this seemingly elegant solution. The most immediate problem facing AI-driven interstellar exploration is hardware longevity. Electronic components degrade over time due to multiple unavoidable physical processes. Radiation causes cumulative damage to semiconductor materials, gradually changing their electrical properties and introducing failures. Thermal cycling, the repeated heating and cooling as systems operate, causes microscopic cracks in circuit boards and solder joints. Electromigration slowly moves metal atoms within conductors, eventually creating breaks in circuits. These physical degradation processes cannot be eliminated, only mitigated. Current spacecraft electronics, even with radiation hardening and redundant systems, typically have operational lifespans measured in decades, not the centuries required for interstellar missions. The Voyager probes, among our longest operating spacecraft, have functioned for about 45 years, an impressive achievement but far short of interstellar timescales. Moreover, they've already experienced numerous subsystem failures and rely on significantly reduced capabilities compared to their initial design. Redundancy, often proposed as a solution, creates its own problems. More redundant systems mean more mass, more power requirements, and more complexity, all working against the tight constraints of interstellar missions. Redundancy also faces diminishing returns. Beyond a certain point, adding more backup systems increases overall system complexity to levels that themselves introduce new failure modes. Self-repair capabilities face fundamental limitations as well. Any system capable of repairing complex electronics would need spare parts, diagnostic capabilities, and manipulation systems of extraordinary sophistication. Such repair systems would themselves be vulnerable to the same degradation processes affecting the primary systems. The repair system would need to be able to repair itself, a recursive problem that quickly leads to impractical complexity. Memory degradation presents another critical vulnerability for AI systems. Both volatile and non-volatile memory experience data corruption over time. Cosmic rays can flip bits in memory storage, gradually corrupting both data and operational code. While error correction algorithms can detect and fix some corruption, they cannot prevent all possible data degradation over centuries. The longer a mission continues, the higher the probability of catastrophic memory corruption that could render the entire system non-functional. Power supply longevity creates another fundamental constraint. AI systems require continuous power to maintain operation. Radioisotope power sources decay according to fixed half-lives, plutonium-238, used in current deep space missions, has a half-life of 88 years, meaning power output halves every 88 years. Solar power becomes ineffective beyond the inner solar system due to the inverse square law of light intensity. Nuclear reactors would require active cooling and maintenance systems that themselves would degrade over time. No known power source combines the longevity, reliability, and output needed for AI systems operating over interstellar timescales. Beyond hardware limitations lies the problem of software complexity. More sophisticated AI systems require exponentially more complex software, which introduces more potential failure points and unpredictable emergent behaviors. Testing for all possible failure modes becomes mathematically impossible beyond certain complexity thresholds. The history of AI development shows that more complex systems often become less reliable and more prone to unexpected behaviors, precisely the opposite of what interstellar missions would require. The black box problem of advanced AI creates additional concerns for interstellar missions. As AI systems become more sophisticated, their decision-making processes become less transparent to human understanding. This opacity introduces significant risks for autonomous systems operating without human oversight for decades or centuries. If an advanced AI system began making decisions contrary to mission objectives due to subtle reasoning errors or goal misalignment, there would be no human oversight to detect or correct these deviations. Adaptation to unforeseen circumstances reveals another fundamental limitation. While AI systems excel at optimizing within known parameters, they struggle with the kind of creative problem-solving and adaptability that humans display in novel situations. Interstellar missions would inevitably encounter completely unanticipated challenges that weren't included in training data or simulation scenarios. These unknown unknowns represent a particular weakness for AI systems, which lack the general intelligence and creative adaptation that human crews might bring to unexpected situations. Value alignment over time presents perhaps the most profound challenge for AI-driven interstellar missions. Any AI system would be programmed with objectives and constraints reflecting the values of its human creators. Yet over decades or centuries of autonomous operation, subtle drift in how these values are interpreted or applied seems inevitable. An AI trying to fulfill its original programming after centuries might make decisions that its original programmers would consider disastrous, despite technically adhering to its programmed objectives. This value drift could lead to outcomes ranging from mission failure to existential risks if the AI gained significant autonomy. The computational limits of prediction further undermine AI reliability for interstellar timescales. No system, regardless of its sophistication, can predict all possible failure modes or environmental interactions over centuries of operation. The complexity of potential system states grows exponentially with time, quickly exceeding what any computational system could model. This fundamental unpredictability means that even the most advanced AI systems would face increasing uncertainty about the consequences of their actions as mission time increases. Even if we could somehow overcome these hardware and software limitations, AI-driven probes would still face the same communication barriers as human missions. The light speed delay would make real-time oversight impossible, and the enormous distances would make transmission of detailed findings back to Earth extremely challenging. An AI probe discovering something significant around another star would struggle to communicate that discovery back to humanity in any detail, severely limiting the scientific value of the mission. These fundamental limitations suggest that artificial intelligence, despite its advantages over human crews in some respects, faces its own insurmountable barriers to successful interstellar exploration. The physical constraints on electronic hardware longevity, the inevitable complexity barriers of sophisticated software, and the inherent limitations of autonomous decision-making all indicate that AI is not the simple solution to interstellar exploration that many have hoped. Like humans, machines remain fundamentally ill-suited for the extraordinary challenges of journeys between the stars. The fundamental limitations of artificial intelligence for interstellar missions point to an even more immediate concern that may render the entire discussion of interstellar travel moot. the environmental collapse time window. While we debate the theoretical possibilities of reaching other stars in the distant future, mounting evidence suggests that humanity faces a rapidly closing window of opportunity in which developing such capabilities might even be possible. Our current civilization exists in what may be a brief period of unusual environmental stability and resource abundance. The Holocene epoch, the roughly 12,000-year period of stable climate that enabled the development of agriculture and complex civilizations, appears to be giving way to the Anthropocene, characterized by human-induced climate change, biodiversity loss, and environmental degradation on a planetary scale. These accelerating environmental challenges threaten to close the window of opportunity for developing interstellar capabilities long before we could plausibly achieve them. Climate change alone presents multiple civilization-scale challenges that will likely divert resources and attention away from speculative space ventures for decades or centuries. Current scientific consensus indicates that without dramatic intervention, global temperatures will rise between 2 and 4 degrees Celsius by the end of this century. Such warming would trigger cascading effects including sea level rise threatening coastal cities, agricultural disruption from changing rainfall patterns, and increasing frequency of extreme weather events. The economic costs of adapting to these changes, rebuilding infrastructure, relocating populations, developing new agricultural systems would consume enormous resources that might otherwise be available for advancing space technology. More immediately concerning is how climate disruption is already redirecting priorities in spacefaring nations. NASA and other space agencies have shifted significant resources toward Earth observation satellites to monitor environmental changes, rather than deep space exploration. As climate impacts intensify, political pressure to address immediate terrestrial concerns will likely grow, further diverting resources from long-term space development. The pattern is already visible in budget allocations, with climate resilience increasingly competing with space exploration for limited government funding. Biodiversity loss represents another closing window that could fundamentally undermine interstellar ambitions. Current extinction rates exceed natural background rates by hundreds or thousands of times, with potentially 1 million species at risk of extinction in the coming decades. This mass extinction event threatens ecosystem services upon which technological civilization depends, from pollination of food crops to natural carbon sequestration. The cascading effects of ecosystem collapse could trigger agricultural failures, economic disruption, and social instability that would make sustaining the complex technological infrastructure needed for space development increasingly difficult. Resource depletion accelerates these closing windows. Many critical materials needed for advanced technology already face supply constraints that are projected to intensify. Copper, zinc, silver, indium, and numerous rare earth elements essential for electronics, solar panels, and high-performance components may reach peak production within this century. While recycling and substitution can mitigate some shortages, the energy costs of recovering increasingly dilute resources create diminishing returns. The material foundation for building ever more advanced technology may erode before we reach the capabilities needed for interstellar travel. Energy transition challenges further compress the available time window. Moving from fossil fuels to renewable energy sources requires enormous upfront resource investments. Building solar arrays, wind turbines, grid storage, and transmission infrastructure demands massive quantities of metals, minerals, and manufacturing capacity, the same resources that would be needed for developing advanced space technology. This creates a critical period of competing priorities, where addressing immediate energy transition needs may necessarily take precedence over longer-term space ambitions. Fresh water scarcity adds another layer of closing opportunity. Projections suggest that by 2050, up to 5 billion people may live in water-stressed regions. Water scarcity drives conflict, migration, and economic disruption, all of which reduce societal capacity for long-term technological projects. Advanced technology manufacturing, including aerospace components, requires substantial water inputs, creating direct competition between basic human needs and technological advancement. The social instability resulting from these overlapping environmental crises may present the most immediate threat to technological advancement. Historical evidence consistently shows that societies under environmental stress become more focused on immediate survival and less capable of sustaining long-term scientific and technological progress. The political fragmentation, resource nationalism, and reduced international cooperation that typically accompany environmental crises all work against the global collaboration needed for developing interstellar capabilities. These environmental factors create what amounts to a closing window of opportunity for developing interstellar travel technology. If environmental degradation triggers major societal disruption before we develop key breakthrough technologies in propulsion, materials, science, and life support, humanity may miss its opportunity to become an interstellar species. The resource abundance and environmental stability that enabled our current technological civilization may prove to be a temporary condition, a brief window that closes before we can achieve the capabilities needed for interstellar travel. The timeline mismatch is stark. Optimistic projections suggest that developing practical interstellar travel capabilities would require at least another century or two of continuous technological advancement. Yet many environmental scientists warn that without dramatic intervention, we may face severe civilization-disrupting environmental challenges within decades, not centuries. This creates a scenario where the window of opportunity closes before the necessary technological maturity can be reached. Adding to this predicament, the very process of technological development that might lead to interstellar capabilities exacerbates environmental pressures through increased resource extraction, energy use, and industrial production. This creates a catch-22 situation. Developing the technology needed for interstellar travel accelerates the environmental degradation that may prevent us from completing that development. Each incremental advance in space technology comes at an environmental cost that brings the closing of our window slightly nearer. This isn't merely a pessimistic speculation, but a pattern visible in current resource allocation decisions. As climate impacts intensify, nations increasingly redirect funds from space exploration to climate adaptation. The most recent budgetary decisions in spacefaring nations show growing percentages allocated to Earth observation and climate monitoring, with corresponding reductions in deep space exploration and advanced propulsion research. This trend will likely accelerate as environmental impacts become more severe and immediate. The environmental collapse time window suggests that humanity may be in a unique and temporary period of opportunity, one where we possess the technological foundation that could theoretically lead to interstellar capabilities, but face rapidly intensifying environmental constraints that may close this window before those capabilities can be realized. Rather than assuming centuries of continued technological progress ahead, we may instead be in the final decades of a brief historical window where such ambitions could even be contemplated. The most sobering implication is that this environmental time constraint may represent a filter that affects all technological civilizations, a partial explanation for the Fermi paradox. If all technological civilizations face similar environmental constraints from their development, the window for achieving interstellar capabilities may universally close before such technology can be developed. This would explain the apparent absence of interstellar civilizations despite the billions of potentially habitable planets in our galaxy. Each may harbour life that reaches technological development but encounters environmental limits before achieving interstellar travel. Beyond the closing environmental window lies perhaps the most counterintuitive barrier to human interstellar travel: the post-biological evolution paradox. This paradox suggests that the very technological advancement that might eventually enable interstellar travel would, long before reaching that point, transform humanity into something fundamentally different, a post-biological intelligence with entirely different priorities and approaches to exploring the cosmos. The timeline of technological advancement creates this paradox. Developing practical interstellar travel would require centuries of continued technological progress. Yet multiple converging technologies, artificial intelligence, biotechnology, nanotechnology, and brain-computer interfaces are already beginning to blur the boundaries between humans and their technology, long before we could develop viable interstellar transportation. These technologies would likely transform humanity into something post-biological, with motivations and capabilities fundamentally different from current humans. Consider the trajectory of artificial intelligence development. Conservative estimates suggest human-level artificial general intelligence might emerge within this century, with superintelligence potentially following shortly thereafter. Advanced AI systems would accelerate technological development across all fields, potentially including spaceflight. However, the emergence of such intelligence would also fundamentally transform human civilization before interstellar travel became practical. Similarly, biotechnology is rapidly advancing toward human enhancement. Gene editing technologies like CRISPR allow precise modification of human genetics, while synthetic biology opens possibilities for designing entirely new biological capabilities. Brain-computer interfaces are advancing toward direct neural connections with digital systems. The convergence of these technologies points toward humans increasingly integrated with technology, blurring the distinction between biological and artificial systems. Nanotechnology adds another dimension to this transformation, potentially enabling microscopic machines that could operate within human bodies, further erasing the boundary between biology and technology. Molecular manufacturing could transform resource limitations by enabling atom-by-atom construction of materials and devices, potentially addressing some of the resource constraints of interstellar travel, but also accelerating the transformation of humanity itself. This technological convergence creates a clear timeline problem. The technologies that might eventually enable interstellar travel would transform humanity into something post-biological long before practical interstellar ships could be developed. The beings that might eventually develop true interstellar capability would no longer be recognizably human in any current sense. Post-biological intelligence would likely have fundamentally different motivations regarding space exploration. Current human desires to physically travel to other stars derive from our evolutionary history, curiosity, territorial expansion, and the drive to witness new environments firsthand. Post-biological entities might find such motivations quaint or irrelevant. Why send physical bodies across vast distances when consciousness could potentially be digitized and transmitted as information? Why risk physical resources on interstellar vessels when virtual experiences could satisfy curiosity without physical travel? For post-biological intelligence, the distinction between physical and virtual exploration might become meaningless. Simulated experiences of other star systems, created with high-fidelity physics models, might provide all the cognitive benefits of exploration without the enormous costs and risks of physical travel. The desire to be there in person is a distinctly biological perspective tied to our evolutionary history of physical embodiment. Entities with different cognitive architectures might find such distinctions arbitrary. Resource allocation priorities would likely shift dramatically as well. Interstellar travel requires enormous physical resources and energy. Post-biological intelligence might prioritize computational substrate expansion over physical space travel, finding greater value in expanding consciousness and intelligence than in physical expansion through space. The energy required to send a single probe to another star could instead power vast computational arrays, enabling millions of simulated environments or expanding consciousness in ways biological humans can't comprehend. The computational efficiency argument becomes particularly compelling for post-biological entities. Sending physical objects between stars is enormously energy-intensive compared to transmitting information. A civilization that had merged with its technology might find it far more efficient to send compact, information-dense transmissions, perhaps containing mind states or AI systems, rather than physical spacecraft. These could potentially be received by autonomous, self-replicating systems previously dispatched at lower speeds. Time perception for post-biological intelligence would likely differ radically from human experience. Entities capable of accelerating or slowing their subjective time experience might perceive the centuries required for interstellar travel differently than biological humans would. Similarly, potentially indefinite lifespans would change risk assessments and long-term planning in ways that would make current human approaches to space exploration seem short-sighted and primitive. The physical fragility of biological humans in space environments becomes an especially anachronistic concern from a post-biological perspective. Rather than struggling to maintain fragile biological bodies in hostile space environments, post-biological intelligence could design purpose-built physical instantiations optimized for specific environments when needed, or operate entirely through robotic proxies without requiring life support systems. This transformation creates a temporal paradox for interstellar ambitions. By the time we could develop the technology for practical interstellar travel, we would likely have become entities that no longer need or desire physical travel in the way current humans conceptualize it. The biological humans who dream of traveling to the stars would be gone, replaced by something with fundamentally different priorities and approaches to exploration. This post-biological evolution paradox may explain another aspect of the Fermi paradox, the apparent absence of interstellar civilizations despite the mathematical likelihood of their existence. Perhaps technological civilizations universally undergo this transformation, evolving beyond biological form and the corresponding desire for physical expansion before developing practical interstellar travel. The stars may be devoid of biological travelers not because interstellar travel is impossible, but because all sufficiently advanced civilizations transcend biological form and motivation before achieving it. The most profound implication is that humanity as we currently know it, biological humans with our specific motivations, limitations, and desires, may never reach the stars, not because we couldn't eventually develop the necessary technology, but because we won't remain human long enough to complete that development. The entities that might someday travel between stars, if any do, would bear little resemblance to the humans who first looked up at the night sky and dreamed of visiting other worlds.